Tes tes. Baik. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Welcome to day 2 of the symposium. We are excited to continue with another series of inspiring talks today. Our first session in second day, we will be chaired by Dr. Widya Budiawan with speaker Dr. Yulia Firdaus. To Dr. Widya, the screen is yours.
Okay, thank you, Miss Fia. Today we have Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Today we will have Dr. Yulia Firdaus will give talk for us. He obtained his doctor in science from KU Leuven, Belgium, and now he serves as a senior research scientist in Research Center for Electronic National Research and Innovation Agency. And today he will talk about the functional interlayer tuning for single junction and multi-junction organic solar cell devices. So are you ready, Dr. Yuliar?
Yeah.
Okay, so you can start your talk.
Okay, I think you have seen my screen already. Okay, thank you, Dr. Widya, for the introduction. Glad to be here to talk in this symposium. We have seen several nice talks yesterday talking about perovskite solar cells. So today I'm going to talk more about organic solar cell, which was my core works during my postdoc at KAUST. So I will talk mostly about the functional interlayers, especially the whole transport layer in single junction and multi-junction organic solar cells. So in the organic solar cells, we typically need two type of materials to be used for active materials. One of them is called electron donor, and the other one is called electron acceptor. The structure itself, essentially, we are using two types of structures. The first one called bilayer, where we have one layer deposited on top of each other. This was developed by Tang in 1986, but the problem with this kind of structure is because of the limitation in the organic semiconductor. Normally we have the exciton diffusion length is quite low, and the thickness is limited, and also then it required charge transport should be high for the transport between the electrodes. On the other hand, after the development of these bilayer solar cells, we also see the concept of this bulk heterojunction, which was developed by Alan Higger in the Santa Barbara groups. And after that, from 1995, it was immediately adopted as the standard structure in the organic solar cells. So as I said, the development of this organic solar cells basically start from this bilayer and the bulk heterojunction concept, especially in the 1995, which was start with the bulk heterojunction concept, providing us with around 1% of efficiency. And at that time, or we can say that the 30 years development of these organic solar cells can be divided into 3 stages. The first stage is when we use these fullerene acceptors. These buckable fullerene acceptors used typically with the polymer donors such as P3ST. And using this P3ST, we can obtain efficiency from 3 to 7%. But the problem with the P3ST is that it has a wide band gap, so it will be limit the absorption, and then also the energy alignment is not really suitable with the most of the fullerene acceptors. So the researchers also try to develop new polymer donors that can be suitable with these fullerene acceptors in terms of the energy level, and it was also developed in terms of the band gap. So more of the narrow band gap polymer donor was developed, and then when combined with this PTB7 PC70BM, it can reach efficiency up to 10 to 11%. So this was the second periods of the development. And then the third development is the more recent development, where the researchers try to develop an alternative to the fullerene acceptor. So that's why this is called the non-fullerene acceptors. And starting from 2015, I think we have seen this kind of structure where the fused ring acceptors like this can reach efficiency over the 11% with suitable polymer donors. And then around 2019, we have seen also this kind of ladder fused ring type non-fullerene acceptors, which give us efficiency over 15%. So now we are achieving efficiency over 20% in the literature using this kind of Y6 derivatives. So the key factor for the success of this non-fullerene acceptor can be classified into these three factors. The first one is, if you can see here, the absorption coefficient of this non-fullerene based active layer, it has a higher absorption coefficient because the non-fullerene acceptor can contribute more to the absorption of the active layer. So it has a higher absorption coefficient compared to the fullerene acceptor. So the active layer absorption coefficient is also higher. And then the second factor is that the synthesis of these non-fullerene acceptors, basically using this kind of A acceptor and then this donor acceptor unit. So we can use like ADA type of molecule, such as the one used here in the ITIC. And by changing the strength of the donor and acceptor unit in this molecule, we can actually tune the energy level of this non-fullerene acceptor. So not only we can tune the HOMO-LUMO of this non-fullerene acceptor, we can also change the molecular packing based on this ICT effect of this donor and acceptor units. As a result, we have typically a planar fused ring molecular backbone. And the consequence of this fused ring molecular backbone, we really see from this Y6 type of monofullerene acceptor, where we have this kind of isotropic molecular packing. So we have this 3D crystal packing of this Y6, as we can see from this work. And the consequence of this observation is that we have this non-fullerene acceptor to be relatively high mobility. So we observe over 10 to minus 3 centimeter square per volt second for this mobility of this non-fullerene acceptor, quite comparable with the fullerene acceptor actually. And then we also observe in recent years that this non-fullerene acceptors is actually has a high exciton diffusion length compared to the fullerene acceptors, and also for most of the conventional organic semiconductor. The consequence of the molecular packing of this kind of non-fullerene acceptor also giving us a lower energy losses in the device when combined with the polymer donor. So the question is how much further we can improve the efficiency of the organic solar cell. So we did some simulation in the past using this ellipsometry measurement combined with the transfer matrix and ripple diffusion simulation. And one of the interesting finding from this simulation is that we can see from this figure, basically when we minimize the non-geometric combination or the bulk recombination in the active layer, basically we can have this decrease in the performance when we increase the mobility of the active layer. So what we found is that when this is the case when we use the non-selective contacts. So if the active layer is too high and the bulk recombination is very low, then the charge will recombine, the minority charge will combine in the wrong electrode. So if we want to keep increasing the efficiency to over 20%, then we need to use the selective contact. So in this case, then we will have the positive effect of this active layer mobility, and over 22% of the efficiency can be achieved by suppressing not only the non-geminate recombination, but also the surface recombination by using the right selective layer. So that's come to our discussion on the desirable material characteristic for interlayer. So not only that we need to have the right energy band level of the interlayer so that we can have the ohmic contact between the interlayer with the active materials, but we need to block also this unwanted charge. So in this case, we can minimize the surface recombination. The other physical characteristic we need is the processing versatility. So we need to have the processing of this interlayer to be more simple. So the more simple it is, then it would be more economic and viable it would be. So the other one is the transparency of the interlayer should be also quite high. In this case, we will have less parasitic absorption, and then we need to have also high electrical conductivity so that the contact resistance or the device series resistance is also will be low. So that's come to the outline of my talk. So I will, in the first part, I will talk mainly about the whole transport layer in single junction solar cells, which was developed in my previous works, and then I will continue with the some discussion in the interlayers in the multi-junction organic solar cells. So the whole transport layer mostly used in the single junction organic solar cell is P.PSS. Even I checked the current record efficiency that was around 20.8%. It was still using P.PSS, but it comes with some problem actually. So with P.PSS, it's normally quite hygroscopic and acidic. So the pH is around 1 to 2 due to the PSS chain here. And it's demonstrated the effect of this P.PSS in the organic solar cell device. So after several days, the device using P.PSS losing in photocurrent compared to when we reduce the hygroscopicity and the acidity of the this whole transport layer by, for example, making this composite of this molybdenum oxide with P.PSS, then we can still preserve better the photocurrent and sustain the device stability of these organic solar cells. So one of the alternative of this or the solution to this problem is to change the properties of this P.PSS by reducing the hygroscopicity or maybe reducing the acidity of these materials. The other way is to find an alternative materials for this whole transport layer. So what we did was, for example, shown in this example of using liquid phase exfoliated 2D materials prepare in solution, and we can prepare the layer of these 2D materials on ITO directly by simple process like spin coating. And when we check on the AFM image, the deposition of these 2D materials on ITO, we barely see any different on the ITO surface when after the deposition of these 2D materials. But the proof of this deposition can be seen from this elemental analysis with the SEM-EDS, where we can see that the tungsten and the molybdenum oxide can be deposited and has been deposited and distributed quite nicely on the ITO. Another proof of this deposition successfully can be seen in this Kelvin probe measurement. So So the work function of this ITO modified by this tungsten sulfide and molybdenum sulfide changed quite significantly after this deposition. And we can also use the density functional theory to estimate the number of layers that we have using this tungsten sulfide. So for this tungsten sulfide, we estimate that the flakes that we deposited on the ITO is around 1 to 3 monolayer, while for the molybdenum sulfide is basically a multi-layers based on the comparison with the of this work function. So then we incorporate this 2D material as an HTL in the organic solar cells. And immediately we can see the effect of these materials, where for the molybdenum sulfide, the performance is less than the reference P.PSS, while for the tungsten sulfide, it gives a higher POC and also better photocurrent compared to the P.PSS, which also confirmed by the external quantum efficiency. So interestingly is that we see also a different kind of interference effect in this organic solar cells when we use the tungsten sulfide and molybdenum sulfide. This can be explained by the photonic structure that is quite different. So in the first case, the P.PSS thin film is probably around 25 nanometer. So compared to the tungsten sulfide or molybdenum sulfide, that is atomically thin layers. So we have in the end a different photonic structure. And then the other type of materials that recently become a hot topic is the self-assembled monolayer. So we have seen this demonstration of the self-assembled monolayer resulting in high efficiency of normal structure perovskite solar cells using this 2PEX molecule. So if you see the absorption coefficient of these molecules in the solvent, it's giving quite low absorption coefficient compared to, for example, another SAMs that is also developed by the same group. So they compare basically these 2PEX with the methoxy based 2PEX, and they from the Kelvin probe measurement they found that the work function of this ITO modified 2PEX giving the most suitable energy level alignment to the perovskite, resulting in higher efficiency of the perovskite using the 2PEX self-assembled monolayer. So this was demonstrated in 2019. Then we were thinking to use this also for organic solar cells. At that time, there is no group reporting these 2PEX for the organic solar cells. So we immediately use this self-assembled monolayer on the ITO and use it for the organic solar cells. And as you can see here, the absorption of the ITO after modified by the 2PEX is not changed dramatically compared to when we use P.PSS. So we have, when we use P.PSS, we will have this kind of parasitic absorption in our device. So that's one of the advantages of using this self-assembled monolayer. In terms of the roughness obtained from the AFM measurements, of course, with the P.PSS, we will have a better roughness, so less roughness, I mean, but with the ITO 2PEX, it is more conformal to the ITO. And the proof of the deposition on the ITO substrates also shown by this EDX analysis, elemental analysis, where the 2PEX has been distributed quite nicely on the ITO substrate. And when we use this for our device, and then we see also this kind of measurement from the photoelectron spectroscopy in air. We measure the work function of these 2PEX, which is also confirmed the previous result that it is changing the work function of the ITO after this modification. And this is suitable for the whole collection of this from this active layer, especially from the donor material PM6. And this also shown by the single junction, single current, single charge carrier device, where we build this kind of whole transport layer on the bottom, and then also another whole transport layer on the top, so to see the injection of this hole in the device. So using the modified ITO, we can see that the hole injection is quite symmetrical, which means that the hole injection from the both sides is quite good. And then integrating this into organic solar cells, we can see that the effect of the 2-packs self-assembled monolayer is very different when we don't use any hole transport layer. So if we don't use any hole transport layer, then we will have a lot of losses from VOC, fill factor, and also GSC. And when we use 2-packs, then we have a better device performance compared to the reference PSS, as also shown by the increase in the GSC and also the fill factor. The GSC also confirmed by this measurement of the external quantum efficiency. So after that publication, we were contacted by the chemists from the group of who developed this 2-packs molecule. So we collaborate with him from Lithuania University, and we try to modify the periphery of this carbazole group. The first one is by adding this bromine atom, and then the other one is with the methoxy unit. So again, here the 2-packs and the brominated and the methoxy giving quite similar absorption, which is also less compared to the PSS. And as you can see also here from the DFT calculation, the effect of this atom by atom substitution is changing quite significantly the electron density in the substituent locally. So, but that's enough to change the work function of the ITO. So we can see here, if we modify the ITO with the brominated 2-packs, then we have the work function around minus 5.7, while for the methoxy is around 4.7. So the difference in the work function will also affect the device performance. As you can see here, the device performance seems like linearly affected by this work function of this modified ITO. And the best performance is obtained by the brominated 2-packs. You can see the efficiency can reach up to 18% with this brominated 2-packs. Another important observation from this study is that when we use these 2-packs to make the device and then measure it, and then we can try to reclaim the substrate by first we try to clean the organic materials and the contact with chloroform bath, and then we clean again the substrate for using soap with and then isopropanol, and then we try to use this oxygen plasma to remove all the organic contaminants on the substrate, and then use it again for the cell fabrication. And what we found is that when we use P.PSS, the reuse P.PSS is performing much less compared to the fresh one. Compared to when we use the brominated 2-packs, we still can reclaim the high efficiency of this device using the brominated 2-packs. I think this is quite expected, as we know that the P.PSS is acidic, so it might also be damaging the ITO layer. So let's move to another type of materials, that is copper thiocyanate. We have seen this copper thiocyanate used in many applications for different kind of optoelectronics application. We have seen in the first application is people using it for the dye-sensitized solar cells, and then we were able to use this in the past for this kind of interesting device structure where we use where we mix copper thiocyanate with PCBM, and then we got this kind of copper thiocyanate mesostructure mixed with the PCBM. So in this kind of device, we have the PCBM as the only photoactive material. What is interesting is when we mix this materials, we can get actually quite nice efficiency up to 5.4% with quite nice fill factor. And then the other application is we use it for a basic study. We know that the copper thiocyanate can give nice PL quenching with most of the non-fluorine acceptors. So we use it for making a bilayer of the copper thiocyanate with the many of the acceptors we have. And then we try to measure the EQ of this bilayer device with different acceptors thickness. As you can see here, we can try then to simulate these to obtain what is the diffusion line of the non-fluorine acceptors from our device. And
okay, 7 minutes more.
Okay. And what is interesting is that we can get this high diffusion line of these non-fluorine acceptors from our measurement, which is also confirmed by another spectroscopic measurement. And then we can also see this application of this photo detector using copper thiocyanate and gallium nitride. Okay, I will skip this. The problem with the copper thiocyanate is normally processed from DAS, but when we use the non-fluorine acceptors and high HOMO level of polymer donor, we normally have this A shape of the JV curve, because what we found is actually the copper thiocyanate process from DES has quite large resistivity. So we try to increase the conductivity of this copper thiocyanate by putting this copper thiocyanate in a dry etching chamber. So we don't use the plasma, we just flow the chlorine gas on this chamber to expose this copper thiocyanate with the chlorine gas and try to increase the conductivity. So what we found here is that the conductivity of this copper thiocyanate can be increased by changing the exposure time. So we use this kind of device structure to measure the conductivity, measure the JV curve here, and indeed the conductivity is increasing by increasing the exposure time, but after some time it's also decreasing. And then this one is showing that the reason why the conductivity is increasing is mainly because of the hole concentration is increasing. So the work function after the chlorine dope CuACN is also changing by the chlorine gas exposure time. So after just few seconds, the exposure time of the chlorine gas is enough to increase the work function of this CuACN. So we try this with different active layer, and this S shape immediately disappear when we use this dope CuACN, and we can increase the efficiency. So we also use this copper thiocyanate for perovskite solar cell. So we can see that the effect of the passivation of this ITO when chlorine is deposited on the ITO, resulting in the reduce of the non-relative recombination. And also when we integrate it with the device, the perovskite device, then the device performance is increasing when we use this kind of dope CuACN. So this was universally shown by the increase is shown universally by using different active layer from organic solar cells, including also the perovskite solar cell. And then maybe this is another work we have done recently. So we use this aqueous ammonia solvent to dissolve several hot transport layer materials. And we use copper thiocyanate, copper chloride, and then molybdenum oxide and vanadium oxide to complexate these materials in ammonia. And the materials after deposited to make a film, then we calculate the band gap is quite large for all of these materials, and then we also try to identify what is the chemical that we obtain from this preparation. And yeah, so the device performance that we got mostly we get better compared to the PSS when we use molybdenum oxide and vanadium oxide. Okay, maybe I will switch gear to the multi-junction organic solar cells. I will not discuss too much in this slide, but what we actually really need for the multi-junction organic solar cell is a good interconnecting layer. So we need to have this interconnecting layer so that we can get the recombination between the hole and the electron from both subcells. And in most of the cases, the interconnecting layer is using this molybdenum oxide. So we need the evaporation. We can also use solution process like the modified P.PSS. So the problem with using P.PSS is it is orthogonal solvent for the active layer, but it has a high surface energy. So we often need to do modification of this P.PSS to have the good wettability on the front cell. So in this work, we tried a different formulation of P.PSS. As you can see, the conventional P dot, it has quite a large contact angle, similar to water, so showing us that this active layer is quite hydrophobic. But when we use this H solar, another formulation of this P.PSS, we can get a lower contact angle, which means the wettability of this H solar is good. This is also confirmed by the optical microscopy here. Using the H solar, we obtain like quite nice film on the so this active layer will be used as the front cell. And also then the injection is also better when we use a good film on the active layer. So we try to incorporate this in tandem cells. Using these two subcells, we can, because of the quality of this interconnecting ligand is good, so we can get a nice tandem cells with a good current matching between the front and the back cells. So we tried also this formulation in three different labs, and the highest reported VCE for this tandem cell is 16.1%, which is much higher than the single junction we use in this work. So we also try to further improve the efficiency by using a better front cell and the back cells, and with the help of this device simulation to get the optimized thickness of the front cell and the back cells thickness, we can push the efficiency to 16.5%. As you can also imagine, if we use this many layers, and then we have to also use the evaporated interconnecting layer, it will be so tedious. So using all the solution process interconnecting layer, it will be more helpful to get faster fabrication. So we also use this to demonstrate that we can easily make this triple junction organic solar cells using three different active layers that can be complementary to each other. And as a result, we are successfully fabricated these tandem cells, which is at that time was one of the highest triple junction solar cells. Of course, with the help of the better active layer, then we can also get a higher efficiency. This is demonstrated in a recent paper about the tandem, where they also get 21.5% of tandem solar cell. This is probably the highest tandem solar cell of organic solar cells in recent years. So as a summary, the recent organic solar cell efficiency are already over 20%, which is driven mainly by the development of the non-fluorine acceptors and the polymer donors. Although the further improvement can be done by pushing efficiency limit which is especially by interlayer engineering. So of course we have to keep in mind that we need a versatile solution process interlayers, and then also appropriate energy level that are essential. All of them are essential for high performance, scalable, and single junction and tandem solar cells. Thank you.
Okay, thank you, Dr. Firdaus, for your nice talk, and it's so interesting. Before I have a question from the audience, so I will ask regarding your low dimensionality interlayer that after graphene, we believe that the low dimension material will be apply for all the electronics devices. But as you know, up to now, we still not shift to a low dimension material. So, what's your point of view for this one?
That's true. I think reproducibility is an issue also with the 2D materials. So 2D materials could be also has different properties depending on how we prepare it. I mean, if you see the literature also, there are different kind of application of 2D materials. So tungsten sulfide, molybdenum sulfide, in some paper they use it as an ETL instead of HTL. So I think that's a sign of we cannot always get the same result when we are process these 2D materials with different synthesis route, for example. So that's, I think, the one of the challenge with this kind of materials compared to when we use P.PSS. So people, that's the reason why people still using P.PSS, for example, because it is very easy. It is very easy to process, and for group that who only wants to obtain high efficiency, then of course it's the right choice, no, to just use the ready interlayer and then just focusing on other part.
In fact, that the P.PSS have disadvantages, but people still use it, right, for high efficiency solar cell.
For this kind of 2D materials, it's not always available for all groups, right? So yeah.
Okay.
So we'll always access but I mean, if we want to consider the industrial scale, then yeah, so we have to think about something that is more sustainable compared to P.PSS.
Okay. Okay. Now let's move to the next question from Dr. Anissa Aprilia from Unpad. So that the organic solar cell already achieve high efficiency up to 20%. And then her question concerned about the stability of organic solar cell. How can its stability be effectively managed, and what are the prospects for its use in sustainable application? And how stable is organic solar cell organic according to the latest research result? Okay.
Okay, thank you, Dr. Anissa, for the question. I think, yeah, this touch a very important aspect of the development of organic solar cell, because what people are now focusing is just the efficiency. So if we I mean, there is also some reports that this high efficiency of organic solar cell is in fact not really stable. So like for Y6, there is a report is not stable for some reason. For example, the N group that can be react at some point. So, but this is something that can be mitigated. So I think there is also some research on finding a more stable materials, and this is also already demonstrated in some papers. I mean, there is this group from Stephen Forrest from US that already demonstrated in Nature paper. I think that they can obtain like quite stable with this long operational performance. So it depends on which material you are using actually. So the prospect in sustainable application, of course, first we have to choose which kind of materials that is still suitable for long stability, but then we have to also think about what we should use it for. I mean, yeah. I mean, if we want to compete with other established technology, maybe it's difficult, but yeah, we have to find a niche market for this.
Okay, thank you, Dr. Firdaus. And we move to the next question from Dr. Rubening. That's your presentation regarding the use of 2D exfoliated layer. So, would you like to explain further why the work function shift downward upon the additional number of layer of tungsten WS2 and MOS2 based on calculation or simulation?
I'm not sure if there is discussion about why the additional number of layers. So I have to read that paper again.
Okay. And then the next question from Dr. Wilman. How is the stability of the metal sulfide modifier to oxidation? And how did you synthesize this sulfide?
Yeah, I think in the paper we also in the study, I mean, we also demonstrated the stability of this tungsten sulfide, which is better than when we use P.PSS. So this is like operational stability inside the vacuum. So we don't do the stability like without encapsulation out in the ambient condition, but mostly we do it in a chamber, vacuum chamber, and then we illuminated it with solar light or LED light, I think LED light, and then we measure it. We measure the operational stability like that. And then this sulfide was synthesized by the liquid phase exfoliation. So I think I will share it again. So yeah, like this. So you use like this sonicated sonication like this. So then we have it is introduced bubbles. So it will exfoliate the bulk like tungsten sulfide to create this nanosheet. So it's quite simple procedure actually, which I think we can also do in Brin. And this was done in a fume hood. So with air condition, we don't need this like inert condition.
Okay, another question from Miss Andi Isni Pujirana. Have you tried characterizing the electrical properties using DLTS to investigate defects trap? So how you, I think before you answer, maybe you can explain how do you investigate the defect traps?
So yeah, I mean, we had planned to use this kind of technique to investigate the defect traps, but even after I left house, I didn't do it in the end. So, but mostly we use another technique to investigate defect traps in the device, not in the material itself. So, in the device we can use like intensity dependent measurements, and then we can use another techniques such as transient photo current transient photo absorption, which indirectly sometimes we can see the effect of these traps in our device, but not
But the DLTS?
No, never.
Oh, never tried before.
Mm.
Okay. I think that's all of the question that in my hand. And then today, this session talk is very nice and very productive. And then I'm so thanks to Dr. Yulia Firdaus for your talk this morning. And then thank you very much. And
Thank you,
we
Dr.
will move to the next presenter. So I will invite Professor Zipeng Fan from Chinese Academy of Science. Good morning, Professor Kan. Ni hao ma?
Good morning.
Chào anh.
Mm.
Okay. I'm so excited that you can join our symposium. Even I'm not become expert, because your topic today is very interesting regarding bilayer organic solar cells. So, bilayer organic solar cell after invention of the bulk heterojunction, bilayer organic solar cell will only few people publish, right? And then before your talk, I will introduce yours. So Professor Sinben Kang from Chinese Academy of Science, China, got PhD in physics, Politecnico in Milano, Italy. And then now conduct as a professor in Guangxi University. And then your publication, a lot of in bilayer solar cell. I think it's very, very precious opportunity to listen your experience in a bilayer organic solar cell. So you can start your presentation. Please,
Okay,
Professor.
so I just share my PowerPoint, right? Document, blah, blah, just a minute. I'll share my screen, Oh. Sorry, just give me a minute. No. Can you give me a guide on how can I share my slides on the screen?
Green share button.
Yeah, I did. Okay, so now screen.
And choose your
Now.
slide.
Okay, now can you see my slides?
Yes, you can make it a slide slow.
Okay, so I put
Okay,
it
thank you.
in
Yeah.
full screen. And okay, good morning, everyone. It's my great pleasure to present our recent results on bilayer organic solar cells here. And also thanks to Dr. Yulia, who sent me the invitation to present this topic and have the chance here. So my name is Zhipeng Kan. I'm working in Guangxi University, School of Physical Science and Engineering. Just now, host already give a brief introduction, so I just want to tell a little more about myself. I got my bachelor degree in Guangxi University, so where I'm working now. It is in the very south part of China, close to Vietnam. And then I moved to Hefei, I got my master degree in Chinese Academy of Sciences. In 2011, I moved to Milan, where I started to work on organic solar cells. Then, after PhD, I went to KAUST. I did my postdoc in KAUST Solar Center, where I meet Dr. Yulia. We were in the same group for more than a year, I think, and then in the center. But I came back earlier than him. I left KAUST earlier than him. By the beginning, when I came back to China, I worked in Chinese Academy of Sciences in Chongqing, and then I moved. Sorry, I laser printer. Then in 2023, I moved back to Guangxi University, where I'm working now. So my research focus in the group is mainly focused on organic solar cells. And as you may know, for now, the most popular used structure is bulk heterojunction active layer structure. Inside this active layer, we prefer to have the acceptor and the donor to form a bicontinuous interpenetrating network, because in this case, when the morphology is fixed, the photophysics property will be fixed. So let's say the exciton generation to charge transfer states, charge separation, charge extraction. But of course, during this process, there are many recommendations. First, the excitons can recombine before they get separated. And also there are geometry recombination at the city states before the the exciton splits into free electron holes and also the non-germinated recombination. All of these recombination will directly affect how the JV curve, let's say the power conversion efficiency then. So for example, exciton recombination will affect the current density for sure. The germinated recombination will affect the fill factor of the device. And then the non-germinated recombination mainly affect the fill factor and the VOC. So in order to improve the device performance and reduce the non-germinated recombination loss, our group focus on mainly these three parts: device physics-oriented work and morphological control in bulk heterojunction to optimize the devices, the morphology, the DA interfaces. Then we also have a part work on device simulation, which also learned from Julia. We did some simulation before together. And then bilayer solar cells, which is the very beginning architecture used for solar cells. Another part is on transporting layers. So like the whole transporting layer and the electron transporting layers. By doping or by modifying the structure, we can introduce different type of dipoles and enhance the charge extraction properties. So today I would like to talk about our findings in bilayer oxide solar cells. So this is the classic paper where in 1985, Professor Tang published the first, let's say, the real meaning solar cell, organic solar cell. In this work, they evaporated the two layers as the active layer and sandwiched between two electrodes. And he found that in this kind of solar cell, the donor and acceptor interface directly determines the device performance. And compared with a single layer solar cell, these bilayer solar cells, the charge generation in this device is independent of the bias voltage. As a result, so he got about 1% efficiency and with a fill factor of 65, which is was really high by that time. But as we also know that because of the limited exciton diffusion length, these layers cannot go very thick. So then the conflict between the photon absorption and the efficient exciton generation or exciton dissociation is the conflict. Then, which means if you go for thicker film for better absorption, the exciton dissociation efficiency will reduce. If you reduce the thickness to guarantee efficient exciton dissociation, but there will be less photons absorbed. So this is one issue by that time. Another issue is the solution processability. For example, here, these two layers were evaporated. So can we really make solution process the devices is a question by that time. And then, of course, bulk heterojunction was invented by Professor Alan Heger in 1995. Then all of us moved to bulk heterojunction. But after 20 years later, in 2020, a German group in Brabeck's group, Professor Brabeck's group, they published a paper on this combination. They used this polymer donor and use chloroform as the solvent to dissolve this polymer donor. And they use IDT derivatives, these small molecules, as the acceptor. They use dichloromethane, DCM, as the solvent to dissolve these small molecules. And they spin coat to fabricate the device in a layer by layer process. So spin coat this layer first in chloroform and spin coat these as a second layer on top in DCM. As a result, they receive this kind of a nice JV curve. Compared with the bulk heterojunctions, we can see that these are really properly performed. So They have a few observations. First is, in their case, they can make the donor layer as thick as 50 nanometers. Then the total thickness of the active layer can up to 100, which is enough for organic active layer to absorb absorb enough photons. Second observation, they found that the photoluminescence spectra of the polymer donor has very large overlap with the acceptors. In this case, if there are this kind of spectral overlap, the Foster energy transfer is involved. So they say that they can have efficient exciton diffusion to the interface and efficient exciton dissociation here. Finally, they got a percentage of 10 in 2010. By that time, this was quite high compared with the very beginning one. And here we can see that, for example, PCBM has less overlap in this spectrum, so the performance was quite low. Then another group in New Zealand, they checked the same structure with a set of materials, and they also got proper bilayer structure with efficient devices. We can see the structure, the cross-sectional structure here, that it is forming of bilayer. So in their case, they also found several interesting things. First, they claim there are long-range exciton diffusion. So for example, for the donor, it goes to up to 60 nanometer thick. So they consider the way why the exciton can dissociate is a long-range threat. They demonstrated this with time-resolved PL and TA spectroscopy. Another thing is they claim there are self-threads within the acceptor layer. So then the excitons can diffuse to the interface, to this interface, and dissociate. An interesting thing is the same. So when the spectral overlap increasing, you see increasing performance. So for example, this is the light blue one. The spectral overlap is the least, so which is performed the worst. In this case, this thread is really playing an important role. Very recently, with the development of these BTP-based materials, the Y6 family, let's say, so the efficiency also improving. And this group, they use green solvents and, of course, different solvents to dissolve the small molecule acceptor and the donor. In this case, they can also fabricate this bilayer structure because of the different solubility of these materials. So in this case, they fabricate both bulk heterojunction and planar heterojunction solar cells. And we can see the performance are really close. And due to the different active layer architectures, we can see that the shape of the EQE also slightly changes. They compared the bimolecular recombination situation and the trap situations. Actually, these two were really the same. And finally, they found that, okay, because of the solubility difference, they can make bilayer solar cells and with all green solvents, and the performance was, the power conversion efficiency was 16 by that time, which was the highest published in that year. So because of the material development, probably Yulia also showed his work, this one. So they determined the exciton diffusion length is near to 50 nanometer. And another thing is in different film formation, let's say bulk heterojunction or neat film, the exciton diffusion length also changes. So now we come back to the question again. So is the exciton diffusion length of acceptor and donor a problem, or if the solution process is a problem? So based on this, we started our work. Before we moved really to the device fabrication, we checked several conditions. First is the molecular weight of polymers. So here we see different vials. Inside, the solvent is DCM, and then the polymers here we used is PM6. So we want to demonstrate that if a proper performing PM6 cannot be dissolved by DCM. So here there are a set of different molecular weight. For example, this one, when synthesized this PM6, the ratio between the two moieties, the BDT and BDD moieties, are different, and the reaction time is less. And then these materials were extracted from hexane, and it can fully dissolve in DCM. With these devices, with these polymers, we can make a device with 16 efficiency. Then, when we increase the molecular weight by changing the ratio, for example, increasing the BDT units and the reaction time, this was partially dissolved in DCM. And with this one, we can have a better performance. And the one we used was usually this one, which has molecular weights around 30,000. So we can see that with this kind of polymer, it will not dissolve in DCM at all. At the same time, we also bought a commercial one, which is this one in this vial, with comparable molecular weight. We see that these materials cannot dissolve in DCM under stirring. And also, we also synthesize the materials with even higher molecular weights, which can only dissolve in chlorobenzene. So in DCM, it's also not soluble. And we see the performance. The best performing devices, PM6, are from this molecular weight range. And this molecular weight range is not dissolving DCM. So which means provide us the evidence that this material, this bottom layer will not be affected by the upper layer deposition. And we did also another very straightforward experiment. We let me see the video if it can play here or not. So what we did is okay, the video didn't work. So I just explain by words. So we put the film, spin coated film. We put the spin coated film directly in the DCM beaker. So by immerse the film inside by 2 minutes, and the film can still alive without change. So that is another way. And then this is the in situ absorbance. So we monitor the absorbance of the polymer donor during the spin coating process. So we can see here in the 2D map, this is the film formation of PM6. And then we use DCM as the solvent alone to wash the film. So we spin coat PM6 film when it's dried, we spin coat DCM on top. And after this wash, we see that actually there's no difference. So which means the DCM didn't remove the PM6. And then we do the same for the upper layer. So we dissolve this acceptor in DCM and spin coat DCM on substrate, spin coat the solution on substrate. We got this film formation process. And then we combine these two together. So we spin coat PM6, we spin coat on top the acceptor layer, and then we use DCM to wash away the acceptor layer. So we see that from the very beginning to the end, the acceptor can be removed, but the donor layer exists, still there. So this is another evidence saying that we are fabricating a bilayer structure. Then we also use the spectroscopy. So this is the cross-sectional SEM images. We send our samples to local testing company, and the particles here we see the round ones are the sparkler, the gold, to have the connectivity. here we can see that from the contrast. By the contrast, it's very obvious. We see two layers here. And then we sent also the samples to Postec in Korea. So there, they helped us to did the cross-sectional SEM again. And we can see from the contrast, the lighter one here, darker one here. It's also a bilayer structure. With this, we also did the cross-sectional TEM, which is in high-resolution TEM. So we sent our samples to Anhui University in China. So they cut the samples with FIB, and then we measured the TEM. In this case, we can also see a clear contrast. Here is more white, bright, and here is more dark. So this difference also tells us that we are really forming a bilayer structure. So based on these, we had a few publications already. By the beginning, we worked on the IDT-based materials the same. So by varying the ionization energy offsets, we checked how is the charge recombination situation in these devices and the charge generation situation. So when we have larger IE offsets, the charge generation efficiency increase with reduced charge recombination. And we also fabricated the as-cast devices by using PM6 and N3. So in these as-cast devices, we see a great efficiency improvement. Later on, we just learned, use what we learned from bulkhead junction. We did a kind of ternary devices. For example, we put PC70BM as the additive in the acceptor layer, and we see dramatic increase in the device performance. So we got 19.5 by that time. And now I would like to explain three recent examples we did. First is on different solvent additives. So since we say it's bilayer, so there are two layers. It provides us more chance to optimize the layer separately. So for example, the donor layer and the acceptor layer. So here we selected the three naphthalene-based high boiling point solvent additive and dissolve PM6 in chloroform, Y6 with DCM. In this case, we first checked the absorbance spectroscopy. So by using different solvent and solvent additives, we see from here that when we put the solvent additive in PM6, actually we see that very tiny changes, which indicates that the film morphology changed very less upon the addition of additives. But when we check the acceptor alone, with and without additives, we see the spectra changes a lot. And so let's say, though the absorbance cannot measure the morphology directly, but it reflects the morphological changes. By checking the peak position and the width ratio, we can get information on if, for example, if the peak move to the red, then it's a formation of J aggregation. If it's moved to the left, it will be a formation of H aggregation, let's say. And then by comparing these, we see that the dramatic change in the Y6 morphology. But how that happened, we monitored this process with in situ absorbance. We can see that when DCM alone was used, there are only two processes, right? So first, we have the signal of the acceptor in solution, and then it immediately dried. So there's no evolution between, but solvent from solution to dry films. And the change is constant here. But when we have these solvent additive inside, for example, this fluoronaphthalene inside, we can see that it's a slow drying process, which is also easy to understand because fluoronaphthalene is a very high boiling point solvent, and it will really make the the process slower. So here, additive induce a slower drying process of Y6 film. What will be the result? So when there's no additive, we see that it's a uniform surface with proper scattering peak here. But when we have additives, for example, fluoronaphthalene, we see the aggregation pattern changed dramatically from uniform to this kind of finger-like aggregations. And the scattering peak also tilted. So not only the fluoronaphthalene, but also chloronaphthalene, bromide naphthalene change. So we all see the tilted scattering peak. We see the different size aggregations. And actually, these are the presence of polymorphs of Y6. So polymorph is like a small, tiny crystals of Y6. So in this case, when we change from different solvents and solvent additive, we see polymorphs, the presence of polymorphs. And these will dramatically increase the device mobility for sure because of the increased crystallinity. And then we fabricate bilayer devices. We see that, for example, take this figure. So here the blue lines are the devices without additive in the accept layer. And these red color are the devices with additive in the accept layer. So the first conclusion, we can see that for sure with the polymorph, with the presence of additives, it improves the device performance. Another conclusion we can get is no matter there are additives in or not in the accept layer, but it doesn't, let's say this way. So no matter there are or there are not additive in the donor layer, the device performance will not change that much, which indicates or which tell us again, the solvent additive is more interaction with the acceptor instead of donor. And we checked the device performance by several techniques. For example, first we check the dark current. We consider it's a diode. So we see that with the additive in the acceptor layer, the dark current is really suppressed, and the series resistance and shunt resistance got optimized. We checked the charge extraction time, so by using transient photocurrents. So the device is held at short circuit condition, and then when a light pulse shine the device, we see the decay, and here will be the amount of charges. So we see the current decay. So in this case, because it's in short circuit, so the faster the decay, the faster the charges are extracted from the device. Then we use transient photovoltaic to check the lifetime. So here the device is held under open circuit. So all the charges generated by the pulse cannot be extracted. They must go for recombination. So the longer they live, the less recombination in the device. So it means when we have additives in the acceptor layer, when we have these polymorphs, we have better charge extraction and long carrier lifetime. And by using this method, we can also apply it to other BTP-based materials. All see these polymorph presence. And in this PM6 BTP EC9 system, we got 18.6%, which with a certified number of 18.2 by that time, which was the highest when we published for bilayer system. And we see that so this method is a widely applicable method to create polymorphs of the small molecule acceptors. Besides these device performance, the device stability also got enhanced, because there's no the thermal and the there's no there's no big blend of donor and acceptor, so it's thermodynamic stable. And with the presence of polymorph, it's even stable than the control devices. Another work I would
5
like
more minutes, Professor.
how many
5
10?
more minutes.
5 more minutes.
5 minutes.
Okay,
Okay,
I will be
5
fast.
minutes.
Another I want to show is we use two additives, which combines two additive in the accept layer to optimize the crystallinity and the orientations. So in this one, when we use different additives, the aggregation feature of L8BO changes, and the orientation of the packing also changed from face on to edge on blend with tiny face on. So with this kind of 3D network, it is more efficient for charge transport. So when we fabricate devices using these bilayer and these additives, we gradually increase the device performance from 17% to close to 19.2% here. And in the EQE, we found that also these parts, the acceptor part, the contribution is really enhanced. So here we also characterize the device recombination situation, the charge extraction, recombination time constant, and the bimolecular recombination rates by CLEAF. We see that with both additives, the recombination speed is really surprised. And here we checked the trap density. This one was using DLTS actually, but it's current-based DLTS to calculate how was the trap situation in these devices with and without additives. This one was calculated from impedance spectroscopy. So in this case, we see that with the additives, we can suppress the charge recombination and reduce the energetic disorder in the layer in the devices, which results in good performance. So here we also monitored how is the device stability. So with the two additives together, the device is very stable even after 1,000 hours operation, and which is still maintain more than 95% of the initial performance. In this method, we also applied to other materials, the BTP-based materials, and we do see the same contribution enhancement in the acceptor part and improved device performance. So this method is also widely applicable to BTP derivatives. Last work I want to show is because we use DCM as the solvent for the small molecule acceptors, and different acceptors has a different solubility inside us. A direct idea is we combine these two materials to tune their solubility inside. In this case, the morphology will be changed. So we see that with addition of BTPEC9 to L8BO, the J aggregation of LABO will increase, and also the crystallinity. So here we see the topography that by adding this BTP EC9, the fiber length and width increase in the thin film, and also the scattering peak enhanced, which indicates a stronger crystallinity. So the improved molecular packing. As a result, so we fabricated the devices, and we do see the contribution in the acceptor part improved, and with 10% of addition BTP EC9 inside, we got the optimum performance, which is 19.7%. And we use this solubility difference method to a set of different materials like ITIC-based acceptor Y6 and polymer acceptors. We all see a similar trend and increase in the device performance, which is wide applicable to all sets of these non-fluorine acceptors as long as they have solubility difference in the same solvent. So by doing that, I introduced the three work which we optimize the accept layer, but we also have the space to optimize the donor layer and the acceptor layer together. So for example, this work is an ongoing one. we can see the changes in the donor range and the fiber length, fiber directions in the acceptor range. And as a result, by optimized device, now we can get more than 20% efficiency, which the certified efficiency by a third party is 19.7%. And with, of course, different type of additives to modulate the aggregation of the acceptor, which is also close to 20%. So for the moment, by controlling the morphology of the acceptor layer and both the together with the donor layer, in the IceCast device, we got 18.1% device, and then by modulating the polymorph, we got improved performance again. Then with this double additive, we increase the device performance beyond 19. Then the solubility difference pushed the number to 19.6, and donor acceptor together, we push it more than 20%. So here is the summary, what we did. And I would like to acknowledge my team members who performed the bilayer work and our collaborators in Postec. They provide great help in GVAX measurements, and collaborators in Tsinghua University in China, and my founding agents. And I would like also to give a brief introduction to a special issue in energy materials. Me and Yulia, we are the guest editor. So we welcome guys to submit work to this special issue. Yes, okay. Thank you very much. Now I finish my talk.
Okay, thank you, Professor Khan, for your nice talk. Very interesting. And then now we have a quick answer discussion session.
Okay.
So regarding the bilayer structure,
Yes.
we should control the molecular alignment in donor and acceptor. So we have already controlled the alignment in the bottom. So we should control together or every layer. Maybe you can.
Okay. I think there are two aspects. First, if we want to form a bilayer, we need really to control the molecular weights for the lower layer. In this case, we need to make sure that the upper solvent do not dissolve the bottom layer. So this is to form a bilayer structure. But to improve the performance, then we can optimize both layers. So then to improve the morphology of both layer, we can get an overall enhancement in the overall devices. So yeah, so there are two reasons, two directions. So to form bilayer structure, we need to control the molecular weights of the lower layer, but to improve the performance, we should optimize both layers together. Okay, did you get what I said?
Yes, Professor.
Okay.
So another question from Dr. Wilman.
Okay.
Do you have any ongoing works in your group to optimize the charge collection from lower wavelength region?
Yes. So we asked some materials from collaborators, which the materials that are light emitting materials, which absorb in between 300 to 450 this part. So we tried to use it as a first additive and also as transport layers. And we do have some progress and with the manuscripts in preparation. So in that case, we can convert more the lights in the lower wavelength to the photocurrent.
Okay, the next question from Dr. Firdaus. So you can talk directly, Dr. Firdaus.
Hello, Khan.
Hi,
How are
hi,
you?
Julia. Yeah, good. Please.
Oh, yeah, I mean, nice collective of works, and maybe I actually interested in the polymer you use. Seems
Yes.
like when you are using very high molecular weight, it start to decrease the performance. I mean, is that just statistical, or there is the trade-off between the molecular weight increase? I don't
Okay.
know.
So,
Or
well, yes, please.
yeah, I mean, uh, or you also maybe should choose like a certain range of molecular weight for the optimized condition, right? I
Yes.
mean, when you purchase the materials, you look into the molecular weight, or I think you will do that, right?
Yes, I see. We did. So here I didn't put the molecular weight is because I didn't get the GPC data for this yet. So this white one, we purchased. So this PM6 here, we purchased from a company, and with the molecular weight about 30,000. With this one is the best performing one on market for the moment, and this one was what we synthesized. So we synthesized with the comparable molecular weights, and you can see the performance is also comparable. As another question on this molecular weight change in the PCE, I think it depends on how we optimize them. So for bulk head junction and bilayer, for the moment, these molecular weights around 30,000 are the good ones. But that doesn't mean this one is the bad one because we didn't really optimize this. We just fabricate use the same protocol. For example, here it can only dissolve in chlorobenzene. It means if we use chloroform for the upper layer, for LABO, this may increase. So there's some more work need to be done.
Also, did you look into the other parameter like polydispersity index, which probably also important, no?
Yes. You mean the PDI, right? How the distribution of the molecular weight, right?
Mm.
So this one we get help from chemists. So they extract the materials with different solvents to make sure that it's, for example, this one they extract this one with DCM, which means the partial can be dissolved in DCM or removed from this. And they extract this one with chloroform, for example. So all the partial dissolved in chloroform is removed from here. So they can guarantee that inside these materials, there's no low molecular weight species.
I see.
So the PDI, they should separate instead of their cross sections.
I think this is also interesting to see if you can translate this into like close to industrial scale, no? I mean, maybe you can try like slot die coating, and yeah,
I need
think
your help, Julia. Let's do that together.
okay, yeah, nice. Thank
Okay,
you.
one more soft question for me. Uh, like 10 years ago, that some group changed the solvent, and then it will be change the orientation of the molecular. So I
Yes.
think it's magic. It's like magic, right? That just change the solvent and then change the orientation. Also, you also using additive, and then the orientation of the molecular is changed.
Yes.
So can you explain in short explanation how it can be?
Okay. Actually, I asked some friends who work on simulation. So their explanation is in the same material, in different solvents, the pre-aggregation tab is different. So if there's already strong aggregation inside the solvent, if I remember right, when we sprinkle or when we cast the film, it will be more agile. If it is less aggregate, when we speak code, we will have more face on. Should be this one, but I do not remember in details. But it really depends on the pre-aggregation situation.
Okay, I got it. Okay, thank you, Professor Khan. Our time for discussion is over now. And then thank you very much for your nice talk, great talk for me. This and thank you. Maybe sometime you will visit Julia in Indonesia, and we
Yeah, I
meet
talked with
here.
him and I
Okay.
said we should, and we will also start to do closely collaborative works. And also, if there are more questions or need, you can just tell Yulia and then email me, or we can get in close contact. So also we have a good, not good, but I mean we have a set of characterization machines on device. So if needed, just ship the samples and we can do the measurements.
Okay, so it should be a great opportunity for us for
Can
to
do.
collaborate with you. Okay, Professor Kang, thank you very much for your talk today. CC.
Okay.
Thank you.
Okay. Thank you. Yeah.
And then
Bye-bye.
now we will have a morning break in 15 minutes. So for
Okay.
participants, we can have a break and see you in 15 minutes. Thank you.
Di kawasan ini terletak laboratorium riset terpadu kami, tempat di mana periset dari berbagai disiplin ilmu bekerja sama untuk memecahkan tantangan kompleks. Laboratorium di kawasan Sains dan Teknologi Samangun Samadikun dilengkapi peralatan canggih yang mendukung riset dalam bidang informasi, komunikasi dan teknologi cerdas, memperkuat sektor transportasi dan teknologi lainnya. Riset kecerdasan buatan, mekatronika dan elektronika di sini mendasari pengembangan teknologi masa depan, memungkinkan Indonesia bersaing dengan sistem artificial intelligence global. Laboratorium di kawasan Sains dan Teknologi Samangun Samadikun juga menjadi pusat riset kegempaan, pemetaan sesar, tsunami, gerakan tanah, serta kajian risiko dan resiliensi bencana untuk mengurangi dampak bencana geologis. Selain itu, riset iklim dan atmosfer yang dilakukan mendukung mitigasi bencana alam, pengelolaan lingkungan, dan pencapaian tujuan pembangunan berkelanjutan. Fasilitas pengujian untuk memastikan bahwa teknologi dan produk baru memenuhi standar kualitas dan keandalan yang tinggi. Di kawasan ini, tempat di mana ide-ide baru lahir. Kolaborasi antara periset, industri, dan mitra internasional menciptakan solusi inovatif yang berdampak luas. Selain itu, kawasan ini dilengkapi dengan co-working space yang dirancang untuk menciptakan lingkungan kerja yang produktif dan kolaboratif bagi sivitas BRIN dan para kolaborator. Fasilitas di kawasan ini telah memenuhi standar pelayanan publik, mencakup tempat ibadah, parkiran, dan toilet khusus disabilitas, tempat menyusui dan daycare, kafe, serta fasilitas kebugaran baik di luar maupun di dalam ruangan. Kami juga menyelenggarakan seminar, workshop, dan pelatihan untuk meningkatkan keterampilan para periset dan SDM pendukung riset, serta berbagi pengetahuan terbaru dengan masyarakat. Kawasan Sains dan Teknologi Samaun Samadikun Bandung adalah salah satu bentuk komitmen BRIN untuk memajukan ilmu pengetahuan dan teknologi di Indonesia. Dengan fasilitas modern dan aktivitas riset yang beragam, kami bertekad untuk menciptakan dampak positif melalui inovasi. Bergabunglah bersama kami dalam merancang masa depan yang lebih baik melalui riset dan teknologi. Kawasan Sains dan Teknologi Samaun Samadikun Bandung, di mana ilmu pengetahuan dan inovasi bertemu.
Research Center for Electronics is part of the Research Organization for Electronics and Informatics at BRIN. The Research Center for Electronics, or RCE, is home to 8 research groups that work together to explore new ideas, develop innovative tools, and contribute to national development through electronic science and technology. Advanced Photovoltaic and Functional Electronic Devices Research Group is one of the research groups in RCE, which specifically focus on the development of photovoltaic and functional electronic devices technology using novel semiconductor materials and the optimization of their fabrication process to obtain highly efficient devices. The objectives of this team are: 1. To bring together a multidisciplinary research team. 2. To be the center of excellence for research and innovation in the field of advanced photovoltaic and functional electronic devices technology. 3. To achieve a combined balance between high-quality science and practical technology as the main research output. This research group is located in KST Samaun Samadikun, Cisitu, Bandung, Indonesia, which is known to be the home of Advanced Semiconductor Device Fabrication Center. At BRIN KST Samaun Samadikun Bandung, a wide range of state-of-the-art photovoltaic device fabrication and characterization facilities are available to support the research and development activities. Together, we aim to build technologies that are not only advanced, but also meaningful and impactful. Electronics is a key area of science and technology that supports many aspects of modern life. In this research group, we believe that the development of advanced photovoltaic and functional electronic devices are essential as the building blocks for determining innovative electronics technology in the future. We also believe that collaboration is central to our work. Therefore, any future collaborations are always welcomed.
Assalamualaikum warahmatullahi wabarakatuh. Welcome back to the symposium. So my name is Wilman Septina. I will be the chair for this session. And so we will begin with the young scientist talks from two young researchers. So the first one will be Anissa Nandita Kurniawati from Institut Teknologi Bandung, and the second one will be from Dr. Junivan from Universitas Indonesia. So in this session, each speaker will have around 10 minutes for the presentation and will be followed by 5 minutes of question and answer. So total will be around 15 minutes. So let's just start the first speaker. So Anissa is actually she's my student here. So she'll be talking about crystallization behavior of ambient air process cesium-lead bromide thin films on various electron transport layers and its impact on solar cells performance. So Anissa, without further ado, the screen is yours.
Okay, thank you so much, Mr. Wilman. Is my voice audible? Okay. Okay, good morning, everyone. First of all, I would like to thank to the committee for giving me the opportunities to talk as a young scientist in the second symposium on Advanced Photovoltaic 2025. My name is Anissa Nandita. I am a master student at Bandung Institute of Technology. Today, I would like to present the research about perovskite solar cell, and the title is of my talk is crystallization behavior of ambient air process CSPBR3 thin film on various electron transport layers and its impact on solar cell performance. So this research was conducted in collaboration with my co-authors, Mr. Iqbal, Mrs. Kartikasari, and Mr. Wilman. And this work is currently under revision in a journal. Okay, next. Okay, in this talk, I will introduce the role of wide bandgap solar cell and wide bandgap perovskite CSPBR3, and then performance of perovskite solar cell affected by ETL. And then I will describe our experimental approaches, result, and conclusion. Okay, next. Okay, wide bandgap solar cell are crucial for tandem architecture because the top cell capture high energy photon, and the bottom absorb the rest of the photon. This is enabling them to achieve up to 30% efficiency. This high bandgap makes them suitable for semi-transparent devices for building integrated photovoltaic. Okay, next. Okay, among all bandgap candidates, I'm sorry, can we refuse? Okay, among wide bandgap candidates, cesium-lead bromide or CSPBR3 stands out with a direct bandgap of about 2.3 electron volt, making it suitable for tandem and building integrated photovoltaic application. We choose CSPBR3 because it can process under ambient air condition and it has high stability. Okay, next. Okay, although the CSPBR3 is promising, its performance is strongly affected by the electron transport layer because the difference in electron transport material strongly influence the crystallization and morphology of CSPBR3 films. And this affecting the device efficiency and stability. In this work, I use 3 electron transport layer. We investigate titanium dioxide and tin oxide, and then indium sulfide. And for this present work, we do fabrication of CSPBR3 solar cell under ambient air condition with high relative humidity were explored. And then the effect of various electron transport layer to crystallization of CSPBR3 and their solar cell are examined. Okay. Next. So here the experimental section, multi-step spin coating in, we do the multi-step spin coating in ambient airs. The first thing we do is preparation of FTO glass, and then we do the deposition of electron transport layer. And for SNO2 and TiO2 deposition, we do the spin coating, while the indium sulfide, we do the chemical bed deposition. Okay, and then next we do the deposition of PBBR2, I'm sorry, for the initial layer of CSPBR3, and then we do the fabrication for multi-step spin coating of CSBR on PBBR2 repeated 8 times to form CSPBR3. And the last step is electrode deposition. We use the carbon, and we can see here, this is the final looks of the solar cell that we make. Okay, next. Okay, this is the characterization of ETL. We first do the SEM. This is the SNO2, ETL, TiO2, and indium sulfide. We can see here all the ETL homogeneously cover FTO layers, and then we do the characterization of UV-Vis. We can see here the peak or the transmittance peak is the same as the bare FTO. It means that they are very thin layer of each ETL and relatively transparent in visible light range. Okay, next. Okay, the next characterization is XRD. We can see here the peak doesn't come off, and it's only the peak of FTO substrate, so it can be concluded that it is very thin film. And the next is Raman. Only the ITO layer that is show the characteristic signal, and SNO2 and indium sulfide didn't show it because it's most likely amorphous and contain very small crystalline domains. And for cyclic photometry, it shows suppressed redox current after ETL deposition, indicating effective blocking behavior. Okay, next. Okay, this is the growth of PBBR2 layers at various ETL. We can see the grain of PBBR2 affected differently on the each of ETL. The first one is on SNO2, the second one is TiO2, and the last one is on indium sulfide. We can conclude here that PBBR2 growth is depending on the underlayer materials, and the growth of PBBR2 appear to be surface dependent. Okay, next. Okay, this is the growth of CSPBR3 after 8 steps of spin coating. This is the grain we can see here is different from each ETL. The big one or the largest grain, it has on TiO2, and the second larger is SNO2, and the least larger is indium sulfide. Okay, next. Okay, this we also do the EFM in order to know the roughness of the CSVBR3 in each ETL. We can see that from SNO2, grain is more roughness more roughness is for TiO2, and for the film of CSVBR3 on SNO2 has balanced grain size and surface roughness for optimal layer. Okay, next. Okay, we also do cross-sectional SEM. In here, it shows that the film on CSVBR3 film on all ETL have uniform thickness, about 500 nanometers, and it can appear that the SNO2 films and indium sulfide film appear smoother and more compact than in TiO2. Okay, next. So here is the XRD of CSVBR3. The pattern we successfully make the pure phase cubic CSVBR3 on all ETL without secondary phase such as CSVB2 BR5 or CS4 PBBR6. Okay, next. Okay, the next characterization of CSVBR3 is photoluminescence, and it shows that SNO2 has the strongest PL, indicating favor defect and lower recombination than TiO2 and indium sulfide. And for ACE characterization, it's still SNO2 have the highest recombination resistance, confirming more efficient charge extraction. Okay, next. So here's the properties of CSVBR3 solar cell that we make. It shows that the solar cell with SNO2 ETL shows the superior photovoltaic properties, and the list that shows the photovoltaic properties is indium sulfide. Okay, next. So this is the best GV curves that we do. We can see that SNO2 has the highest efficiency with 5.05%, and TiO2 3.44%, and the last is indium sulfide 0.70%.
Anissa, one more minute.
Okay, yes, sir. The superior performance in here of SNO2, because it has a larger grain and flat, compact morphology that support efficient charge transport and reduce recombination. Okay, next. Okay, for the summary, CSVBR3 films were successfully fabricated by multi-step spin coating of PBR2 and CSVR, followed by annealing and ambient air with various electron transport layer. Okay, the characterization and morphology of PBR2 layers and consequently CSVR3 are strongly determined by the ETL. And for the last, smooth and compact layers with big grain size with SNO2 layer lead to better crystallization, efficient charge transport, and reduced recombination losses. Okay, next. We also like to thank to all the co-writers here, and the founding of this research is REEM LPDP. And next, for more information, you can contact me or Mr. Wilman Septina. Okay, thank you.
Okay, thank you, Anissa, for your nice talk. So now the presentation is open for Q&A. So we'll still have few more minutes for
Thanks.
those who wants to ask. So Anissa, maybe I will lead the Q&A first. So yeah, I know that I'm involved a lot in this study as well, but based on your experience, so you show a sensitive effect of ETLs to the cesium lead bromide. But how about the sensitivity of the fabrication process itself? For example, during the SNO2, is that also a sensitive? I mean, the fabrication process to the next steps?
While I do the work research in here, I think it's also affected the growth of CSVBR3 because when we do the wrong step or while we annealing the ETL, we didn't do the temperature right or the time right. It can be affected to the growth of CSVBR3, or it can be affected to the efficiency too. I think it can be affected, Mr.
So it's very sensitive as well. Okay.
Yes, and the humidity, relative humidity is also be affected, I think, because we do the relative humidity at under 50%. It has a good efficiency, while we do the fabrication at the highest relative humidity. That's not really good efficiency.
Okay. Okay. So there is Miss Dr. Yulia raised his hand. So please, Dr. Yulia.
Okay, thank you, Mr. Chairman. Okay, nice presentation, Dita. I want to ask you whether if you have tried bilayer ETL, for example, titanium oxide with tin oxide, maybe?
No, I haven't tried it yet. maybe just compact TiO2 and mesoporous TiO2, but it's not
So
really good, Mr.
ETL, I mean the single layer,
Yes.
they are really cover all the FO, or some pinholes also can be seen.
Yes, Mr. I'm sorry,
So
Mr.
you mean
Ilya, I didn't hear you clearly.
So for titanium oxide and tin oxide, do you still see like pinholes? I mean, do you still see like this can be optimized further or not?
Maybe for the pinhole, it doesn't really show any much because when we do the SEM, it cover all the FTO. But on CSVBR3, there are some pinhole in layer in TiO2, ETL, and indium sulfide. For SNO2 ETL, it doesn't show any pinhole, Mr.
Okay, thank you.
Okay, maybe one last questions. Please explain from Enda from UNEG. Please explain. Wait. Please explain how do you judge the higher intensity in PL data expressing lower defect? How do you judge that the higher intensity is correspond to lower defect?
Okay, for PL maybe. In PR, the strongest PL and higher recombination resistant measure in SL2 is indicating favor non radiative pathways. I think it's the wavelength in here that we know that SNO2 has the favored defect and lower recommendation than ITO2 and indium sulfide. And actually, I don't really know much about the photoluminescence. Maybe I will have study more about how do we more about photoluminescence. Thank you.
Okay. Okay, thank you, Anissa. Due to the time limit, so we have to end your session. So if you can answer the question. So there are several questions on the chat box. You can also type on the chat box the answers. Okay, thank you once again, Anissa, for a nice talk. So second young scientist talk will be from Dr. Junifan. So Dr. Junifan is from Universitas Indonesia. So he will be talking about improving ambient process carbon-based perovskite solar cells using copper thiocyanate additive in carbon electrodes. So Dr. Junifan, are you there already?
Yes, yes.
Okay. Okay, Dr. Junifan's screen is yours.
Thank you very much.
I cannot hear your voice, Dr. Junifan. Can you increase your voice or?
Can you hear me now? Can you hear me?
Try again.
Can you hear me?
Yeah, I can hear you now.
Okay.
Go ahead.
Okay. Okay, it's okay now.
Yeah, go ahead. I can
Okay,
hear
thank you very much. Thank you very much, Mr. Wilman. My name is Junifan Sulistianto from Universitas Indonesia. Now, I will present our works regarding perovskite solar cell during my doctoral study in collaboration with Shizuoka University in Japan. In here, I will present the carbon-based perovskite solar cell using copper thiocyanate additive in carbon electrode. Please next the slide. Yeah, so maybe I will not deep insight into how perovskite solar cell works because it's already explained by previous presenter very nicely. Now our focus in research is in the counter electrode of perovskite solar cell because the electrode, usually using noble metals such as gold, silver, or aluminum, because of high conductivity and high reflectivity, and it also will increase the overall performance of the device. And the challenge of the noble metal may be already discussed in the previous talk, because it is need a deposition method that requires high energy and not suitable for large area application, and therefore, and also there is a diffusion phenomenon of diffusion of gold and silver into the perovskite layer, reaction with iodine in the perovskite material, and therefore lowering the stability of the device and shortening the device lifetime. So in here, the research on alternative material for counter electrode is needed. Please, next slide. Yeah, we choose carbon because it is alternative material for counter electrode. It has a comparable work function with gold and has a Hall selectivity. But the thing is, it has lower conductivity than most metal, and also because although it has ability to as Hall transport material, so there is a structure that has Hall transfer free, Hall transfer layer free carbon-based perovskite solar cell, but it has a low Hall selectivity compared to conventional Hall transport material. Please next. So the motivation of this research is to improve the performance of carbon-based perovskite solar cell by incorporating copper thiocyanate into carbon electrode, and also the objective is to fabricate and then investigate the effect of the adding copper thiocyanate into the carbon electrode, and also to evaluate the photovoltaic parameters of the sample with copper thiocyanate and without copper thiocyanate in the carbon electrode. Please next. Yeah, this is the structure of the solar cell that we made. So we have the NIP carbon-based perovskite solar cell without additive and with additive, and the right side of the figure is the energy level alignment sourced from various literature. And in here we use FTO as the substrate, and then TiO2 as the electron transport layer. Perovskite usually we use NaPbI3 and copper thiocyanate as gold transport layer. Please next. And this is the experimental. So we need first to prepare the FTO substrate by etching the FTO layer to separate the anode and cathode contact, and then we deposit the TiO2 layer by using spray pyrolysis for the compact TiO2, and for the mesoporous TiO2 we use spin coating method. Please next. And then for the perovskite layer, we use a two-step method. The first step is depositing the PbI2, and then the second step is by spin coating the MAI into the PbI2 layer. In this layer, we choose two-step method because we have already done some works regarding the ambient process perovskite solar cell. In ambient process in high humidity setting, using two-step method is giving more higher efficiency than the one-step method deposition. Please next. And then for the copper thiocyanate interlayer, we use copper thiocyanate dissolved in diethyl sulfide, 35 milligram per milliliter, which is already optimized by another researcher. And then for the carbon electrode, we make the carbon paste by ourselves using PMMA as the binder, and also the solvent is chlorobenzene. And also the carbon source is using acetylene black, mixture of acetylene black and graphite. And then for the deposition, we use a Doppler blending method. And then for the copper thiocyanate, carbon with copper thiocyanate, we add dipropyl CuSCN in dipropyl sulfide solution into the carbon paste, and then we deposit using the same method. And in the right side, we can see the visual of the carbon-based perovskite solar cell that we fabricate of this. And here is the performance of the device that we fabricate. For the whole transport layer free carbon-based CPSC, we get the efficiency is very low, 0.58, around 0.58%. But when we add CWSCN as the whole transport layer, so the structure will be NIP, not whole transport layer free again. We get the efficiency is significantly higher for around 4.5%, with maximum efficiency around 6.58%. But when we engineer the carbon layer using the solution, CWSCN solution into the carbon electrode, we get the significant increase again on the efficiency to 8.55%, and with maximum efficiency of 11.09%. So the key is when we add CWSCN, either it is as a whole transport layer or as additive, it's increase the efficiency. So the transport layer between perovskite and carbon is improved. Please next. And this is the cross-section SEM image of the device that we fabricate. The left one is the transport layer free, so we can see the layer of its material, and then we can compare in the middle and in the right side of the device. We can see that the device in the right side, when we add carbon with CWSCN additive, the copper titanium layer is significantly the thickness is significantly increased than without a modified carbon electrode. This is because the content of the CWSCN inside the carbon base. And also we propose that the carbon particle is diffused into the CWSCN layer. Therefore, the performance of the modified carbon electrode is higher than without a modified carbon electrode. So please next. And this is the
yes. 1 more minute, please.
Okay, yeah, this is the EDS, distribution of CWSCN inside the carbon, in the bulk of the carbon layer. We can see the deposit of the CWSCN in the base of the carbon layer. It's mean the CWSCN accumulates in the bottom of the carbon layer. Please next. And this is the photoluminescence spectra to study the charge extraction between the perovskite layer itself, and then perovskite with the CWSCN whole transport layer, and perovskite with CWSCN, and also modified carbon electrode. And we can see the lower photoluminescence spectra belong to the device with modified electrode. This means the most efficient charge extraction and the least recombination in the device. Please next. And the conclusion, we already fabricate the proposed carbon-based perovskite solar cell using CWSCN as additive, and from the measurement we can see the increase of the efficiency from 0.5% to 6.58% to 11.09%. Thank you very much. I will give back to Mr. Wilman.
Okay, thank you, Dr. Jonifan, for a nice talk. So we'll open the Q&A sessions. So there is one question on the chat box from Dr. Bening. So thanks, Dr. Jonifan. How would you explain thicker CWSCN layer on modified carbon condition, cross-section SEM? Was copper thiocyanate CWSCN precipitated down, separating itself from carbon base?
Yes. Yeah. Can I share the screen? Maybe I can show the. I will share my screen. So maybe this is the proposed mechanism. Yeah, I think we and Mr. Wening have same idea. So maybe the solution from the CWSCN inside the carbon base is seep down into the interface of the carbon layer. Therefore, the thickness of the CWSCN is thicker in the modified carbon electrode. So it is like we get like mesoporous CuSCN and carbon is like compact TiO2 and mesoporous with perovskite. I think the mechanism is similar like that.
Okay, thank you. So questions from Dr. Yuliar as well. So you mentioned the problem with work function of carbon-based electrode. Have you measured the work function of CuSCN modified carbon electrode? Is it changing? Also, what about the concentration of CuSCN you use? Adding too much probably will decrease the conductivity.
Okay, thank you. Yeah, in this research, we don't have opportunity to check the work function of the modified carbon electrode, but this is also already in my mind when I doing the research, but because of the limitation in the equipment, so we don't check the work function. But other researcher also have a similar trending. So when they add some material into the carbon electrode, it will change the work function of the carbon. So maybe here also the work function of the carbon also different when we add CuSCN inside the carbon. And also, yeah, it's
Okay.
also increasing the CuSCN thickness, maybe also decrease the conductivity. But in here we can see the benefit of the thick CuSCN when we make this device.
Maybe you can mention also about the concentration you use for the optimized condition here.
So I add around maybe around 10% from the. So I use chlorobenzene as the solvent, and then I add 10% of CuSCN solution into the solvent for the carbon base.
So you mix it with the solvent for the carbon.
Yes, with the chlorobenzene. So also, and then I add the solvent I add into the carbon mixture, the carbon powder with the binder in there.
But did you try a different concentration for the optimization?
Yeah, maybe this is our next step for the optimization, because the previous work in this work I use only use I compare DPS and then also DES for the solvent for the CuSCN into the carbon electrode.
So for this work you use only one concentration.
Yes, for the DPS I use only one concentration, but on DES I use several concentration from 10% until maybe around 30%. Yeah, but using DES is not so good because it's strong solvent. DES is strong solvent for CuSCN, so when I add a little amount of CuSCN into the DES, it wash out the CuSCN layer in the HTL layer.
Okay, sorry, Dr. Junivan, I have to stop your session to do the time limit. So thank you very much, Dr. Junivan. So there is one more question from and there are two more questions on the chat box. So if you have time, please reply by chat in the chat box.
Okay, thank you very much.
Okay, thank you once again, Dr. Junivan, for your contribution.
Thank you very much.
So next, we will have the invited talk. So delivered by Professor Joo-Min Kim from Hangkyong National University of South Korea. So good morning, I suppose, or good afternoon there.
Hello.
Yeah.
Could you hear my voice?
Yeah, I could hear you.
Thank you so much for invitation. I'm gonna share my presentation on this slide.
Yeah, I will introduce you first to the audience.
Okay. Thank you.
Okay, thank you, Professor Kim. So before we begin, so let me introduce first Professor Joo-Min Kim. So he is now associate professor in Department of Chemical Engineering of Hangkyong National University in South Korea, and also he is the head of Central Laboratory in the university. So before this position, He was a GSPS postdoctoral fellow in Toin University of Yokohama, Japan, and also special researchers in the University of Tokyo, Japan. So you will have around 30 to 35 minutes, Professor, and then followed by Q&A. So total maybe around 45 minutes.
Okay,
Yeah.
thank you
So
so
you
much
may,
for
yeah, you may share your screen.
Okay, thank you so much for your kind introduction. And
Yeah.
my name is Kim-in Kim. And yes, and I just realized that my presentation is about 30 minutes. It's quite long. So actually, I kind of want to draw the title like this: The Advancements in Perovskite Solar Cells from Dopant-Free Whole Transfer Materials to Stability-Enhanced Hybrid Perovskite. So today, I'm not going to just talk about just one topic, but I'm going to just talk about overall the research that I have conducted for several 3 or 4 recent years. But before I move on, I slightly want to introduce myself again. After I graduated on my master degree in South Korea in Sogan University, I moved to the Japan for my PhD. And after the PhD, I joined the JSPS under the Miyasaka Tsutomu, who is the first perovskite solar cell inventor. So I was conducting the perovskite research with Professor Miyasaka, and I'm still researching the perovskite solar cells with the Professor Miyasaka. And after my postdoc work, I moved to the South Korea on 2020, which is called the Hangyeong National University. And now the 5 years has already passed, and I'm now associate professor in Hangyeong National University.
Sorry, Prof. Kim, I have to pause your session. Could you make a full screen, or here it shows two
Really,
screens.
really? Okay.
Yeah.
Yes,
Could you
that's
maybe.
yeah, that's probably okay. Then I'm gonna share the different screen.
Yeah.
Okay. What about now? Is it okay now?
Yeah, it's good now. Yeah.
Okay.
Thank you. Sorry to
So
interrupt. Go
yeah,
ahead.
thanks for and so the Hangyeong National University is located in the place called the Ansong. I probably think many of you guys do not know about the Ansong, but many of you know about the place called Seoul, which is the capital of South Korea. And this is actually the South Korea. And as you know, this is in North Korea, this is South Korea. And South Korea is a very small country, and this is Japan. The South Korea is just right next to Japan. And Seoul is here, and Ansong is here. Ansong is here. So Ansong is around like 1.5 hours from Seoul. So if you have any chance to come to Seoul, just please let me. If you want to see the campus of the Hangyeong National University, you're just free to contact me, and I'm going to tour our campus. And actually, our campus is quite small, but has many departments. But half of departments is actually engineering departments, and I belong to the chemical engineering department. And actually, the Ansong, the place in Hangyeong National University, is really famous for a very delicious the food. And actually, many of the Korean ramen is made in Ansong. Actually, Ansong has mega ramen factory. I guess you may know about this Shin Ramen, and that's actually very big Shin Ramen factory right next to my campus, and you can actually tour the ramen factory. And alongside ramen, actually we have variety of Korean traditional food. And I guess the in Indonesia, soto ayam is quite famous, which is my favorite. But in Ansong, we also have very famous soup, which is called the 국밥. So if you come near here, I want to treat you this 국밥, which is very traditional Korean kind of the soto ayam. And the small even though my campus is quite small, our campus recently launched the research center, which has variety of experimental tool. And especially because I study about the perovskite solar cells, we recently launched many experimental tools regarding the perovskite research, including the sputtering system and XPS, and also the dry room and the automatic thermal evaporator and E-beam sputtering and ALD system. So now our research group can also study about the perovskite tandem solar cells, which require this E-beam and ALD system. And since yesterday, many of the professor and the researchers already explained about the history of the perovskite solar cells. So today I'm just gonna skip about the history of the perovskite, but I just want to emphasize that now the perovskite power conversion efficiency of the single cell is already reached over 27 power conversion efficiency, which is really high compared to the silicon-based solar cells. And because of the progress of the structural evolvement, the perovskite solar cell mostly starts from these dye-sensitized types, but now many of the groups just use this, the very simple structure of the cells. And nowadays, many of the groups already reached the theoretical limits of the current value, but still many groups cannot reach the maximum voltage actually. So the increase in the voltage is the key to high power conversion efficiency even nowadays. And the fast development of the power conversion efficiency in perovskite solar cell is because of this decompositional engineering. And the perovskite actually consists of these ABX structures, and each ABX site can, more than 2 atoms can be incorporated in each site. And nowadays, many of the groups already use more than 2 cations in A site and more than 2 or 3 halide anions in X site. But unfortunately, the change of the B site is quite challenging because the B site, the B site ion actually affects the energy level so deeply. So changing the elements of the B site is really careful. So today I kind of want to focus on the manipulation of the B site by incorporating this germanium ion into the lead. By the time around like 2020, I could not really see the research regarding the germanium added perovskite solar cells. I only found the 2 papers about germanium doping into the perovskites, but most of the perovskite solar cells, the all inorganic perovskite solar cells are studied. I could not find any organic-inorganic hybrid perovskite solar cells by using this germanium iodide in near the 2020 and 2021. So there were no reports regarding the organic-inorganic based lead germanium hybrid perovskite. Why? And by when I just try by doping about this germanium into the perovskite precursor, I just found out the reason why. If we just dope this germanium iodide in the perovskite precursor, we can actually face very poor of the solubility in perovskite precursors. So we cannot really get the high quality of the perovskite films. But I found another extra way. When I include this methyl ammonium chloride in the perovskite precursor solution, the solubility suddenly improves so much. So we can actually dissolve this germanium iodide into the perovskite precursor solutions by using this methyl ammonium chloride. So we can actually get very clear films by using this germanium iodide with this methyl ammonium chloride additives. And by increasing the dopant levels, the film color actually changes. And I actually check this germanium doped perovskite films by checking these IV curves, and I could find the gradual increase in the VOC is observed in this germanium doped organic inorganic hybrid solar cells. So I could obtain more than 22.7% by doping this germanium iodide. And another effect of this methyl ammonium chloride, including this germanium iodide, is that methyl ammonium chloride significantly reduces this oxidation of germanium iodide. Actually, this germanium iodide is easily oxidized from this Ge2 plus to Ge4 plus. And after the oxidization, mostly the color of the precursor changes to the brown color. But when there's a methyl ammonium chloride in the precursor solutions, we cannot see any change of the color, which means that this methyl ammonium chloride not only improves the solubility of this germanium iodide, but also prevents the oxidization of this germanium iodide. But those days, I could not really find the reason why this methyl ammonium chloride improves the solubility of this germanium iodide. So after I come back to South Korea, I further studied about this germanium iodide, especially into the tin lead-based inverted perovskite solar cells. So now I kind of want to change my topics to the this lead tin germanium triple B cation inverted perovskite solar cells. So in this case, I also try to use this germanium iodide with this methyl ammonium chloride, but maybe for the researchers who study about this tin lead perovskite in inverted structures, actually we need the guanidium cyanide as an additive. Without this guanidium cyanide, the tin fluoride, tin iodide is easily oxidized and the performance is not really good. So mostly this inverted tin lead perovskite structures, we mostly use this guanidium cyanide plus actually the tin fluoride. But in my case, I tried to use this germanium iodide into the perovskite precursor solution. So to improve the solubility of this germanium iodide, I had to use this methyl ammonium chloride. But as I mentioned, this guanidium cyanide is really necessary in these inverted structures. But when I use this guanidium cyanide and methyl ammonium chloride at the same time, always the performance is really poor. So in that time, I actually tried to remove this guanidium cyanide and just use this methyl ammonium chloride only. And surprisingly, the performance is mostly similar to the guanidium cyanide. So I just realized that this methyl ammonium chloride is really effective in this lead tin perovskite to prevent the oxidization of the tin iodide and also the guanidium, also the germanium iodide. And the interesting fact is that when I use this germanium iodide in the DMF solution, if the time pass out, the color actually changes to the brown color, which means the germanium iodide is oxidized. But as I mentioned, this methyl ammonium chloride can prevent the oxidization of this germanium iodide. And also actually the guanidinium cyanide itself also prevents the oxidization of the germanium iodide. But as you can see, when I dissolve this germanium iodide in the precursor solutions, we can actually see the slightly yellow color, which reflects the germanium iodide. But when I use this methyl ammonium chloride, the precursor solution becomes very clear. So which means that this methyl ammonium chloride can form some kind of the intermediates with this germanium iodide. As you can see here, this is this germanium iodide, but when I add the methyl ammonium chloride, the absorbance peak of the precursor solution shifts to the blue shift. So I further characterize by checking the XPS and XRD. And when I use this methyl ammonium chloride in the germanium iodide, I just realized that there's a halide exchange between the chloride and iodide, and the methyl ammonium iodide related intermediate phase is formed, which is really soluble in the perovskite precursor solutions. So in this research, we found out that the methyl ammonium chloride can form the intermediates by changing the halide exchange. So just like the previous my reports, this inverted structure, the 3% of the germanium iodide is very optimal because it still shows clear perovskite films, which means that the solubility of the germanium iodide is quite good. And the perovskite grain size and the surface morphology is really good when the 3% of the germanium iodide is used. And the interesting fact is that, once we make the perovskite films with the germanium dopants, the perovskite peak actually XPX-XRD peak actually shift to the low angle, which means that the crystal light is expanded. Expansion of the crystal light is is occurring by using this germanium. Because the size of the germanium, it is reasonable that the crystal is expanded. But the interesting fact is that when the sample is aged to the 7 days and 14 days, the perovskite peak slightly shifts to the large angles, which means that the gradual contraction of the grain size is occurring. And so I kind of speculate that the germanium iodide is moving toward the surface. And then the contraction of the crystallization and crystal structure is occurring actually. So this scenario is occurring for whole concentration of the germanium iodide. But in the 3% cases, after the 7 days, the crystal of the perovskite is quite stable. There's no gradual the peak shift of the XRD for the 3%. But when it comes to 5 or 7%, even the XRD peak is further shift to the large angle, which means that the even further contraction of the crystal is happening. I do not really know the reason why, but anyway, the 3% of the germanium iodide doping in the perovskite precursor solution is the optimum condition. And actually, we also checked the top sims measurement. That we just realized that the germanium concentration is moved toward to the surface by aging, which means that the germanium ion is migrating onto the top surface by aging. So anyway, by using this germanium iodide into the lead tin-based perovskite by resorting to the tin lead germanium triple B cation perovskite solar cells, could record over 20% of the power conversion efficiency, recording almost 30 milliampere per square centimeter, which is quite larger than just tin lead perovskite solar cells. And actually, this tin lead based perovskite solar cells is easily oxidized by oxygens, but by using this germanium iodide, we can actually suppress the degradation of the solar cells incredibly. And this is the MPPT, the result. Okay, now I kind of want to also change to my topics to the passivation layer. And nowadays, many groups in these conventional structures, we mostly use the passivation layer in between the perovskite and spiral layers. And by the time in 2022, the phenylethyl ammonium halide was the most popular passivation layers. So I also use this phenylethyl ammonium bromide on top of the perovskite as a passivation layer. And of course, I could see the high power conversion efficiency by using this phenethylamine bromide compared to the without phenethylamine bromide device. But in fact, after 2 or 3 days, I could not see any power conversion efficiency difference. And I think many of the groups already realize that the IV curve actually changes by over time because of the oxidization of the spiral. So to study about the role of the passivation layer, we should not use this spiral because spiral is also changing. So we cannot really study about the real mechanism of this phenethylamine bromide because of the change of the spiral. So to study about the role of this the passivation layer, our group newly synthesized the HTL to replace the spiral materials, and this is the new material of the HTL1. And actually, this the small molecule doesn't require any oxidization steps, so the performance doesn't change by over time. So I synthesize this material and I use this material to check the role of the passivation layer. And the interesting fact is that this new material, without any the passivation layer, the performance is really poor. But with this phenethylamine bromide, the performance is really good. So this material is really adequate to study about the role of this phenethylamine bromide because it also doesn't change any IV curve over time. So I kind of wonder how this phenethylamine bromide works in these cells. Probably is it because of the interface between the perovskite and phenethylamine bromide, or the interface between the phenethylamine bromide and HTL? And I was very curious about which interface is really critical. So I intentionally block the interface by using this PMMA layer. And here, this is the condition 1. I intentionally block this interface to check the interface between the HTL and PEABR. And in the condition 2, I block the HTL and PEABR interface to check the interface between the perovskite and PEABR. And in condition 3, I block both sides. So this phenethylamine bromide cannot interact with either with this interface and this interface. But surprisingly, in all conditions, the solar cell works really good. As I mentioned, without this phenethylamine bromide, the cell is really poor. But in these 3 cases, all conditions, the cell works really fine. So, which means that this phenethylamine bromide, the role of this phenethylamine bromide is not about the passivation of the surface. So I kind of the check of the role of phenethylamine bromide and check the UPS spectrum and the surface potential, and realize the surface potential the significantly changes by using this phenethylamine bromide, which actually changes the HOMO level of this perovskite layer, which means that the function of this the phenethylamine bromide is not about the passivation layer, but about the dipole moments. So in this paper, I firstly report about the role of this passivation layer as the formation of the dipole moment, not about the surface defect passivation. So here is the thing. Probably by intentionally block the interface in between the passivation layer and perovskite might be efficient. So I check the device by deliberately blocking the PMMA layer in between the perovskite and PABR. And in this case, the initial performance is quite similar, but the air stability is really good by blocking the interface between the perovskite and phenethylamine bromide. And I checked the reason why, and I just realized that this phenethylamine bromide gradually reacts with the perovskite layer if there's no blocking layer in between the perovskite and PABR. And I further study how the reaction occurs. And we just realized that the lead iodide in the perovskite coming up to the surface, and then PbI2 reacts with this PABR by forming the Pa2PbXI2Br, which is the 2D perovskite, which can be confirmed by the XRD. So actually, the formation of this 2D perovskite on the surface is not really good as a passivation layer. So it is much better just to block the interface between the perovskite and phenethylamine bromide. But I kind of want to emphasize that I only focus on the phenethylamine bromide cases. But nowadays, many papers says that other kinds of the passivation layer, the formation of the 2D perovskite on the surface is really good. So we actually have to distinguish the role of this passivation layer. One is the formation of the dipole moment, and the second is the formation of the 2D perovskite. And we actually have to differentiate the role of this the passivation layer. Okay, now I also kind of want to change my topics to the dopant-free Hall transport layers. And since 2020, I try to synthesize the new HTL by replacing the spiral O method, because spiral method is quite unstable because of the oxidization step, and also the price of the spiral method is quite expensive. So we need some cheap and stable HTL. As you can see, also the spiral method actually requires the dopant such as the lithium TFSI and the TBP, which makes this HTL very unstable. So we should not use this the dopant in new HTL. So this is the concept. This is our new HTL. we actually synthesize this molecule. And as you can see here, we actually incorporate this the alkali metals in molecule itself. In the spiral cases, actually, we use this lithium metal as a dopant. But in our new HTL, we use this metal directly connected to the molecules. And by using the several synthetic routes, we actually synthesize several kinds of the dopant-free HTL, the sodium, the potassium, rubidium, and cesium cases. So we synthesize these 4 molecules and then try to dissolve these molecules to the precursor in chlorobenzene or IPA. And this type of the molecules is well dissolved in the chlorobenzene, but it is not dissolved in the alcohol base. So actually this is really good because I wanted to use this HTL as conventional structure. We coat this material on top of the perovskite, but if it's dissolved in the IPA is not really suitable on top of the perovskite. So the solubility in chlorobenzene is really good cases. And we check all kinds of the 4 molecules, the cesium incorporated, rubidium, potassium, sodium incorporated small molecules. And we found out that the cesium and then rubidium has strong interaction with the perovskite, which reflects the shift of the binding energy of the perovskite peaks. Okay, I'm just going to pass on that one. And surprisingly, the spiral is the dopant one. But this AOC series, this new HTL is not a dopant one. This is the dopant-free HTL. And all these 4 shows quite good efficiencies. But among the sodium, potassium, rubidium, cesium incorporated small molecules, the cesium incorporated small molecule shows the best efficiency over 20% of the power conversion efficiency, which is quite comparable to the spiral method. So now in our group, we use this AOC cesium dopant-free HTL in conventional perovskite solar cells. And okay, let's move on to the anti-solvent method. Oh, now how many minutes do I have now? Okay, so nowadays
maybe 4 more
okay.
minutes.
Yeah. Now many groups actually use the anti-solvent by using the perovskite layer, but when we use the anti-solvent, many of the group use large amount of the anti-solvent, which is around like 200 microliter, sometimes 300 microliters. So in that case, if we make the device in the glow box, the concentration of the anti-solvent gradually increase by over time. So the sample that were fabricated for the first time, the sample that were fabricated the last time, the performance is really different because the concentration of the anti-solvent increase inside the glow box, which affects the performance of the solar cells. So actually the minimization of the anti-solvent is really important. So in our group now recently replaced the DMSO to the NMP in the precursor solution, and we just realized we can significantly reduce the amount of the anti-solvent up to the 30 microliter. But in our group, we really wants to decrease the amount of the anti-solvent to the 8 microliter. And we found something very interesting. When we actually increase the relative humidity up to the 30% in the glow box, we can actually reduce the amount of the anti-solvent to the 8 microliter. And just imagine, many of the groups use the 300 microliter of the anti-solvent, but actually 8 microliter is enough, which is less than 3% of the 300 microliter. So we can actually reduce the amount of the anti-solvents by using the NMP and this relative humidity up to the 30%. So by reducing the amount of the anti-solvent, and our group recently also synthesized a new HTL-free materials. So by combining this new molecule with this low anti-solvent method, we could obtain more than 20% of the power conversion efficiency. And this is also our recent topic. Now our groups actually use the perovskite powder. Many of the groups actually try to prepare each cation, like A site cation, B site cation, and halide cations in to prepare the precursor solution. But actually, it takes a lot of time, and sometimes some students make wrong amounts. So nowadays, our group tries to make the perovskite powder by using this ball milling. And nowadays, many groups use the methyl ammonium chloride as an additive. So our group tries to make perovskite powder, including the additives. Actually, many of the groups already study about the perovskite powders, but our group firstly report the additive included perovskite powders by using the ball milling. And through the optimization, we could obtain pretty good perovskite powders. And this perovskite powder result in a very good performance. And the good thing is that if we use the perovskite powder, we don't actually use the stirring bar. This is very fine powder. So once we dropped the DMF and NMP mixed solvent, we just mix. We just shake with the hands, and within 1 minute, it fully dissolved actually. So our students just use the hands by shaking just 1 minute, and then you can actually fabricate the perovskite precursor solution very easily. And using this method, actually, our group also try to make the spiral and dopant powder. Not mostly the lithium TFSI is used as a dopant, but lithium TFSI is also mixed with the spiral to make the spiral dopant mixed powder. So now by using this optimization condition, we use the perovskite powder and the dopant included spiral powders. So by using this lithium doped spiral powder and methyl ammonium chloride contained perovskite powders, we could obtain more than 25% of the power conversion efficiency. And actually, not only about the high power conversion efficiency, but by using this powder, we can prepare the precursor solution very, very quickly. So today, actually, I talk about many subjects. So for commercialization, actually, we have to go to the organic free and lead free and dopant free. So probably the doping of the germanium might be the key to reduce the lead content. And then the development of the new HTL is the key for the dopant free HTL. And our group is quite small groups, and here are my students to conduct the research. Thank you for the listening. Thank you so much.
Thank you. Thank you very much, Professor Kim, for a very interesting talk with diverse topics in your group. It's very interesting. So I will open the Q&A session. So we still have plenty of times. Let me see. Maybe I will start with questions from me, Professor Kim. So your last works, the perovskite powders, is very interesting. So how did you, I mean, in the details, how did you synthesize the powders itself? So after it makes into a powder, does it needs to be processed under a controlled environment, for example, glove box, or
You're right.
you can store the powders? Yeah, the careful, is it to be needed to be careful storage or something like that?
Right.
Yeah.
Actually, now this paper is in the revision session, so I didn't really explain in detail, but actually it's really easy. We just use the ball milling, but we have to use the liquid actually. We have to input the liquid inside the ball mill. We actually use the cyclohexane. Cyclohexane is not reactive to the perovskite powders. And then by using this additive to make the perovskite powder, the speed of the rotation and then the number of the ball is really critical. So this is all about the optimization. So we found the optimization condition. Without the optimization, the perovskite powder is not soluble at all. But with this whole the optimization process, by adjusting the number of the balls and then the weight of the balls and then the number, the amount of the liquid, and that the time of the ball milling is really important. And after that optimization, we actually proceed the ball milling for 12 hours. And after 12 hours, we moved we remove the liquid and then get the perovskite powder. And that's how we got the perovskite powder.
I see. So, and then after that, is it spin coated?
Right. So once we get the perovskite powder like this, the interesting thing is, this is the perovskite powders we obtained from the ball milling, but this already contains the methyl ammonium chloride. But without methyl ammonium chloride, the perovskite powder is yellowish powder. But by adding the methyl ammonium chloride, the perovskite powder becomes really black. Even this is the powder phase. This is actually the black phase. So we use this black-based perovskite powder just directly onto the perovskite precursors. And this is really well soluble, very, very well soluble. Just, dropping the precursor solution, it just dissolved right away.
I see.
Yeah.
Thank you. Very interesting. So,
All right.
questions from Dr. Yuliar in the chat box. So, is the cyclohexane used for the wet milling will not affect the film quality?
Yes, right. Actually, it doesn't affect any quality of the perovskite. We actually compare with the conventional method, and we cannot find any difference between just conventional perovskite precursor and the perovskite precursor containing the perovskite powder. Even nowadays, the perovskite powder shows a little bit better power conversion efficiency, and we don't really know why the powder shows the better performance.
Okay, thank you.
But cyclohexane is not the perovskite cation and halide, the ions does not react with the cyclohexane, because cyclohexane is really non-polar solvent, and the perovskite, the cation and anions are very polar material. So very polar material with very non-polar cyclohexane does not react at all. And this cyclohexane just helps to well mixed in ball milling process. So we believe that the cyclohexane just helps the mixture of the powder.
I see. And then later you you remove the cyclohexane.
Yeah, right. And cyclohexane is really volatile, so it's really easy to remove after the process. And once we just open the lid and then drop the pressure, and within 20 minutes, all the cyclohexane is gone. It's because it's really volatile solvent.
Okay, thank you. Thank you. So next questions from Dr. Bening. So thanks, Dr. Kim. Very great research question that drive your past and current works. It is interesting that you isolated interfaces when you wanted to know about the effect of PEABR, perovskite / spiral interlayer or passivation. How did you deposit PEMA insulating layer? Would it affect other layers when you apply it?
Yeah, actually, the PMMA is actually dissolved with the chlorobenzene. So we dissolve the PMMA in the chlorobenzene and around like 30 milligram per milliliter concentration, and we spin coat. And after that, we have to anneal the sample because after the annealing, the PMMA is well attached on top of the perovskite. So after the annealing, even though we drop the chlorobenzene on top of the PMMA layer is not removed actually. So after the PMA coating, and to check the PMA layer is fully covered on top of the surface, we actually check the IR spectrum and the surface. We already studied about the surface, the analysis, and the PMMA layer is intact on top of the perovskite after annealing. So that's how we actually coat the PMMA layer.
Yeah. Okay, thank you.
Yeah.
From Dr. Maria, thank you for the great presentation from Gyumin. Have you ever tried the tin germanium base only? I'm just curious if the germanium incorporation will make the tin base easier to fabricate.
Yes, it's really good question. Actually,
without the lead. Yeah.
Yes, actually we tried, but probably our group doesn't have any technique about the tin 100% solar cell. Still, we have very poor power conversion efficiency if we just use the tin 100% cells. So now actually we face some difficulties. So we got very poor efficiency of about 100% tin one, and also tin germanium one doesn't really get the good efficiency. And maybe this is because we could not really optimize the tin based perovskite solar cell. But this is actually our next my next the research about germanium tin perovskite solar cells. And after we get some good results, I'm going to share the results with you.
Yeah, thank you. So next, from Ms. Eka. So Prof. Kim, regarding MACL advantages in perovskite solar cell, is it recommended to use it as solvent and binder solution of photoanode, mostly TiO2 in dye-sensitized solar cell?
Okay, regarding MACL advantages, use it as a solve.
So this is for
Yeah, actually,
TiO2 fabrication, I believe.
okay. I actually didn't really get the points. Actually, could you explain a little bit more detail about
Maybe she wants to know whether MACL also has advantage when fabricating TiO2.
Okay, actually,
So other use of the MACL.
yes, absolutely, because in the lead germanium cases, I use this one on top of the tin oxide and TiO2, and both really works well. This NaCl content precursor is coated on top of the tin oxide and TiO2, and the methyl ammonium chloride contained precursors are coated on top of the PDA-PSS. So I guess this methyl ammonium chloride contained perovskite precursors is working on in many of the layers, including the TiO2 and tin oxide, even in the PDA-PSS. And now many groups use the same layer, self-assembly monolayer. And now our group actually use the self-assembly monolayer. And the MACL contained perovskite precursor works really good on top of the same layer.
Okay, I hope it answers Ms. Eka questions. Still have a few more minutes. So I think from me maybe. So the lattice construction mechanism, is it induced by light or by is it where you observe this? Is it when you shine and measure the solar cells, or
Yeah,
just
right.
storage? Yeah, just storage
It's a
is
good point.
also in use.
Yeah, right. But in this paper, actually, it's just stored in ambient condition without the illumination, actually. So it happens even without the illumination. But recently, we just realized that under the illumination, this facilitates actually so fast.
Oh, I
Yeah,
see.
yeah, right. So this is induced by the heat and also the illumination, I think. But once the contraction happens, and then the crystal lights stabilized after the contraction of the contraction of the crystal lights.
Okay, thank you. So maybe last question from Dr. Yuliar. So any reason why P.PSS still used as HTL here, while normally for MAPI or FAPI it is not used anymore because giving lower performance? Yeah,
it's really good. This one, it was published actually on 2024, but it was studied around like 2020 and 2023. In that time, the tin-based perovskite doesn't work on TiO2 and SiO2 at all. So, our group is specialized in the titanium oxide and tin oxide one, but if we use the tin-based perovskite, the perovskite precursor doesn't work in the metal oxide. So we have to use the organic molecules on below. And actually, we used the PTAA and other layers on that day, but we actually faced the big challenge about the wettability. In the PTAA, many groups reports it's really good, but in our group, the perovskite precursor cannot really the coated on top of the PTAA because of wettability problem, but PWPSS is really good for wettability. So that time the students just want to make a very fast results. So that is the reason why we use the PWPSS. But now actually we use the self-assembled monolayer nowadays. So today I didn't really report the results, but by using the STEM layer to replace the PWPSS, we could obtain more than 23 or 24%. So now I think the STEM is the key to high power conversion efficiency. Yeah.
Yeah, thank you. Maybe very last short questions from me. So your routine fabrication process is now done inside a glove box or dry box? Because I know you want to remove the chlorobenzene as much as possible.
Right.
Is it under,
Right.
because you show comparisons,
Yeah,
dry
right.
box and glove box.
Now we have both system. We have a dry room and the glove box. And when we use the tin based perovskite, we have to use the glow box because the tin is really sensitive to the oxygen. But when we do not use any tin or germanium, we use the dry box actually. Because dry box, we don't need to use the nitrogen. Nitrogen is quite expensive. I just want a cheap dry air. So the students who don't use the tin or germanium, they use the dry box. And the students who use the tin and germanium, they use the glow box. But in any cases, we use a very small amount of anti-solvent. So I kind of want to say one good thing actually. The reduction of the anti-solvent is really good for reproducibility actually, because many students actually make the hole inside the substrate. If you use the large amount of anti-solvent, some students make big hole in the center of the perovskite during the dropping. But if you use very small amount of anti-solvent, which is 8 microliter, even the new student do not make any hole, and they can make pretty good perovskite. So so I think the reproducibility is much more advantage than the concentration of the chlorobenzene in my opinion.
Okay. Due to the time limitation, so we have to end your session. It's very insightful talks, Professor Kim. So thank you very much once again for your contribution. I hope in the future, we can collaborate probably, or you can come to our institution in Frin.
Thank you so much for
this.
Thank
you once again, Professor Kim. So let's give a virtual applause to Professor Kim.
Thank you so much.
So we'll now have a break for lunch. So we will come back at 1:30 p.m. Okay, so thank you.
Kawasan Sains dan Teknologi Samaun Samadikun Bandung, sebuah pusat inovasi dan riset unggulan di Indonesia. Di sini masa depan ilmu pengetahuan dan teknologi dirancang dan dikembangkan melalui fasilitas mutakhir dan aktivitas riset yang beragam. Di kawasan ini terletak laboratorium riset terpadu kami, tempat di mana periset dari berbagai disiplin ilmu bekerja sama untuk memecahkan tantangan kompleks. Laboratorium di kawasan Sains dan Teknologi Samangun Samadikun dilengkapi peralatan canggih yang mendukung riset dalam bidang informasi, komunikasi dan teknologi cerdas, memperkuat sektor transportasi dan teknologi lainnya. Riset kecerdasan buatan, mekatronika dan elektronika di sini mendasari pengembangan teknologi masa depan, memungkinkan Indonesia bersaing dengan sistem artificial intelligence global. Laboratorium di kawasan Sains dan Teknologi Samangun Samadikun juga menjadi pusat riset kegempaan, pemetaan sesar, tsunami, gerakan tanah, serta kajian risiko dan resiliensi bencana untuk mengurangi dampak bencana geologis. Selain itu, riset iklim dan atmosfer yang dilakukan mendukung mitigasi bencana alam, pengelolaan lingkungan, dan pencapaian tujuan pembangunan berkelanjutan. Fasilitas pengujian untuk memastikan bahwa teknologi dan produk baru memenuhi standar kualitas dan keandalan yang tinggi. Di kawasan ini, tempat di mana ide-ide baru lahir. Kolaborasi antara periset, industri, dan mitra internasional menciptakan solusi inovatif yang berdampak luas. Selain itu, kawasan ini dilengkapi dengan co-working space yang dirancang untuk menciptakan lingkungan kerja yang produktif dan kolaboratif bagi sivitas BRIN dan para kolaborator. Fasilitas di kawasan ini telah memenuhi standar pelayanan publik, mencakup tempat ibadah, parkiran, dan toilet khusus disabilitas, tempat menyusui dan daycare, kafe, serta fasilitas kebugaran baik di luar maupun di dalam ruangan. Kami juga menyelenggarakan seminar, workshop, dan pelatihan untuk meningkatkan keterampilan para periset dan SDM pendukung riset, serta berbagi pengetahuan terbaru dengan masyarakat. Kawasan Sains dan Teknologi Samangun Samadikun Bandung adalah salah satu bentuk komitmen BRIN untuk memajukan ilmu pengetahuan dan teknologi di Indonesia. Dengan fasilitas modern dan aktivitas riset yang beragam, kami bertekad untuk menciptakan dampak positif melalui inovasi. Bergabunglah bersama kami dalam merancang masa depan yang lebih baik melalui riset dan teknologi. Kawasan Sains dan Teknologi Samangun Samadikun Bandung, di mana ilmu pengetahuan dan inovasi bertemu.
Research Center for Electronics is part of the Research Organization for Electronics and Informatics at BRIN. The Research Center for Electronics, or RCE, is home to 8 research groups that work together to explore new ideas, develop innovative tools, and contribute to national development through electronic science and technology. Advanced Photovoltaic and Functional Electronic Devices Research Group is one of the research groups in RCE, which specifically focus on the development of photovoltaic and functional electronic devices technology using novel semiconductor materials and the optimization of their fabrication process to obtain highly efficient devices. The objectives of this team are: 1. To bring together a multidisciplinary research team. 2. To be the center of excellence for research and innovation in the field of advanced photovoltaic and functional electronic devices technology. 3. To achieve a combined balance between high-quality science and practical technology as the main research output. This research group is located in KST Samaun Samadikun, Cisitu, Bandung, Indonesia, which is known to be the home of Advanced Semiconductor Device Fabrication Center. At BRIN KST Samaun Samadikun Bandung, a wide range of state-of-the-art photovoltaic device fabrication and characterization facilities are available to support the research and development activities. Together, we aim to build technologies that are not only advanced, but also meaningful and impactful. Electronics is a key area of science and technology that supports many aspects of modern life. In this research group, we believe that the development of advanced photovoltaic and functional electronic devices are essential as the building blocks for determining innovative electronics technology in the future. We also believe that collaboration is central to our work. Therefore, any future collaborations are always welcomed.
Dye-sensitized solar cell is one of the newest third-generation solar cell technology. Just like photosynthesis in plants, DSSC uses dye molecules to absorb light and then convert them into electricity through photoelectrochemistry. The key benefits of DSSC modules are clean and sustainable. The DSSC in this innovation runs on solar energy, which provides clean, endless power since it is the most abundant source of energy in the universe. So you will never run out of energy as you can charge anytime, anywhere, wherever there is light. Affordable. DSSC module uses much cheaper materials than the conventional crystalline silicon-based solar panels. DSSC can also be produced using simple processes in a typical lab without the need of high vacuum equipment. Flexibility. Unlike conventional PV, DSSC not only works under direct sunlight but also works under artificial light indoors and even on cloudy days. It can also be made in various sizes, colors, transparent, and even flexible. Integration. DSSC can be applied in building integrated PV, providing energy in smart buildings, yet with an aesthetic visual. It can also be integrated into IoT and electronic devices and various smart gadgets in your daily life. The integration opportunities for DSSC are endless. DSSC, a device that charges with light, not only better for you, but also for the environment.
peserta research assistant di sini. Dan yang saya sekarang yang meneliti nanti tentang sel surya. Kita sebut jalan. Jadi sel surya, karena kita hidup di negara yang lebih tropis yang memiliki matahari 12 jam, jadi kita harus meneliti mengenai sel surya atau device yang dapat menghasilkan energi listrik dari cahaya matahari. Nah, yang kebetulan untuk saya sendiri itu riset tentang material dari si sel surya tersebut, yaitu material perovskite. Tapi lebih spesifiknya itu menggunakan inorganic perovskite solar cell. Yuk, aku biar tahu cara bikin solar cell.
Step pertama adalah untuk mengambil prekursor dari glove box dengan hati-hati karena prekursornya sangat rentan terhadap oksigen, sehingga harus di-store di dalam glove box sehingga diambil. Nah, setelah diambil, step berikutnya adalah untuk mendeposisi prekursor kepada substrat sehingga menghasilkan lapisan-lapisan sel surya tersebut. Dideposisikan menggunakan spin coater. Untuk caranya adalah untuk meneteskan beberapa tetes dalam substrat kemudian di-spin sehingga menghasilkan sebuah lapisan tipis. Kemudian lapisan-lapisan berikutnya dideposisi dan juga dipanaskan di atas hot plate untuk membentuk film tipisnya. Step terakhir adalah mendeposisikan lapisan kontak, yaitu menggunakan karbon, sehingga akhirnya terbentuk sel surya yang nanti akan diuji dengan menggunakan solar simulator.
Gimana kalian semua setelah melihat ini? Apakah tertarik mengikuti program Research Assistant? Jika tertarik, klik di bawah sini. Dan kalian bisa mendapatkan banyak ilmu dan pengalaman dari periset-periset di BRIN.
Kawasan Sains dan Teknologi Samaun Samadikun Bandung, sebuah pusat inovasi dan riset unggulan di Indonesia. Di sini masa depan ilmu pengetahuan dan teknologi dirancang dan dikembangkan melalui fasilitas mutakhir dan aktivitas riset yang beragam. Di kawasan ini terletak laboratorium riset terpadu kami, tempat di mana periset dari berbagai disiplin ilmu bekerja sama untuk memecahkan tantangan kompleks. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun dilengkapi peralatan canggih yang mendukung riset dalam bidang informasi, komunikasi dan teknologi cerdas, memperkuat sektor transportasi dan teknologi lainnya. Riset kecerdasan buatan, mekatronika dan elektronika di sini mendasari pengembangan teknologi masa depan, memungkinkan Indonesia bersaing dengan sistem artificial intelligence global. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun juga menjadi pusat riset kegempaan, pemetaan sesar, tsunami, gerakan tanah, serta kajian risiko dan resiliensi bencana untuk mengurangi dampak bencana geologis. Selain itu, riset iklim dan atmosfer yang dilakukan mendukung mitigasi bencana alam, pengelolaan lingkungan, dan pencapaian tujuan pembangunan berkelanjutan. Fasilitas pengujian untuk memastikan bahwa teknologi dan produk baru memenuhi standar kualitas dan keandalan yang tinggi. Di kawasan ini, tempat di mana ide-ide baru lahir. Kolaborasi antara periset, industri, dan mitra internasional menciptakan solusi inovatif yang berdampak luas. Selain itu, kawasan ini dilengkapi dengan co-working space yang dirancang untuk menciptakan lingkungan kerja yang produktif dan kolaboratif bagi sivitas BRIN dan para kolaborator. Fasilitas di kawasan ini telah memenuhi standar pelayanan publik, mencakup tempat ibadah, parkiran, dan toilet khusus disabilitas, tempat menyusui dan daycare, kafe, serta fasilitas kebugaran baik di luar maupun di dalam ruangan. Kami juga menyelenggarakan seminar, workshop, dan pelatihan untuk meningkatkan keterampilan para periset dan SDM pendukung riset, serta berbagi pengetahuan terbaru dengan masyarakat. Kawasan Sains dan Teknologi Samaun Samadikun Bandung adalah salah satu bentuk komitmen BRIN untuk memajukan ilmu pengetahuan dan teknologi di Indonesia. Dengan fasilitas modern dan aktivitas riset yang beragam, kami bertekad untuk menciptakan dampak positif melalui inovasi. Bergabunglah bersama kami dalam merancang masa depan yang lebih baik melalui riset dan teknologi. Kawasan Sains dan Teknologi Samaun Samadikun Bandung, di mana ilmu pengetahuan dan inovasi bertemu.
Research Center for Electronics is part of the Research Organization for Electronics and Informatics at BRIN. The Research Center for Electronics, or RCE, is home to 8 research groups that work together to explore new ideas, develop innovative tools, and contribute to national development through electronic science and technology. Advanced Photovoltaic and Functional Electronic Devices Research Group is one of the research groups in RCE, which specifically focus on the development of photovoltaic and functional electronic devices technology using novel semiconductor materials and the optimization of their fabrication process to obtain highly efficient devices. The objectives of this team are: 1. To bring together a multidisciplinary research team. 2. To be the center of excellence for research and innovation in the field of advanced photovoltaic and functional electronic devices technology. 3. To achieve a combined balance between high-quality science and practical technology as the main research output. This research group is located in KST Samaun Samadikun, Cisitu, Bandung, Indonesia, which is known to be the home of Advanced Semiconductor Device Fabrication Center. At BRIN KST Samaun Samadikun Bandung, a wide range of state-of-the-art photovoltaic device fabrication and characterization facilities are available to support the research and development activities. Together, we aim to build technologies that are not only advanced, but also meaningful and impactful. Electronics is a key area of science and technology that supports many aspects of modern life. In this research group, we believe that the development of advanced photovoltaic and functional electronic devices are essential as the building blocks for determining innovative electronics technology in the future. We also believe that collaboration is central to our work. Therefore, any future collaborations are always welcomed.
Dye-sensitized solar cell is one of the newest third-generation solar cell technology. Just like photosynthesis in plants, DSSC uses dye molecules to absorb light and then convert them into electricity through photoelectrochemistry. The key benefits of DSSC modules are clean and sustainable. The DSSC in this innovation runs on solar energy, which provides clean, endless power since it is the most abundant source of energy in the universe. So you will never run out of energy as you can charge anytime, anywhere, wherever there is light. Affordable. DSSC module uses much cheaper materials than the conventional crystalline silicon-based solar panels. DSSC can also be produced using simple processes in a typical lab without the need of high vacuum equipment. Flexibility. Unlike conventional PV, DSSC not only works under direct sunlight but also works under artificial light indoors and even on cloudy days. It can also be made in various sizes, colors, transparent, and even flexible. Integration. DSSC can be applied in building integrated PV, providing energy in smart buildings, yet with an aesthetic visual. It can also be integrated into IoT and electronic devices and various smart gadgets in your daily life. The integration opportunities for DSSC are endless. DSSC, a device that charges with light, not only better for you, but also for the environment.
Purnomo dan saya salah satu peserta riset asisten di sini. Dan yang saya sekarang diteliti nanti tentang sel surya. Kita sebut jalan. Jadi sel surya, karena kita hidup di negara yang lebih tropis yang memiliki matahari 12 jam, jadi kita harus meneliti mengenai sel surya atau device yang dapat menghasilkan energi listrik dari cahaya matahari. Nah, yang kebetulan untuk saya sendiri itu riset tentang material dari si sel surya tersebut, yaitu material perovskite yang tapi lebih spesifiknya itu menggunakan inorganic perovskite solar cell. Yuk, masuk lab biar tahu cara bikin solar cell.
Step pertama adalah untuk mengambil prekursor dari glove box dengan hati-hati karena prekursornya sangat rentan terhadap oksigen, sehingga harus di-store di dalam glove box sehingga diambil. Nah, setelah diambil, step berikutnya adalah untuk mendeposisi prekursor kepada substrat sehingga menghasilkan lapisan-lapisan sel surya tersebut. Dideposisikan menggunakan spin coater. Untuk caranya adalah untuk meneteskan beberapa tetes dalam substrat kemudian di-spin sehingga menghasilkan sebuah lapisan tipis. Kemudian lapisan-lapisan berikutnya dideposisi dan juga dipanaskan di atas hot plate untuk membentuk film tipisnya. Step terakhir adalah mendeposisikan lapisan kontak, yaitu menggunakan karbon, sehingga akhirnya terbentuk sel surya yang nanti akan diuji dengan menggunakan solar simulator.
Gimana kalian semua setelah melihat ini? Apakah tertarik mengikuti program Research Assistant? Jika tertarik, klik di bawah sini. Dan kalian bisa mendapatkan banyak ilmu dan pengalaman dari periset-periset di BRIN.
Kawasan Sains dan Teknologi Samaun Samadikun Bandung, sebuah pusat inovasi dan riset unggulan di Indonesia. Di sini masa depan ilmu pengetahuan dan teknologi dirancang dan dikembangkan melalui fasilitas mutakhir dan aktivitas riset yang beragam. Di kawasan ini terletak laboratorium riset terpadu kami, tempat di mana periset dari berbagai disiplin ilmu bekerja sama untuk memecahkan tantangan kompleks. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun dilengkapi peralatan canggih yang mendukung riset dalam bidang informasi, komunikasi dan teknologi cerdas, memperkuat sektor transportasi dan teknologi lainnya. Riset kecerdasan buatan, mekatronika dan elektronika di sini mendasari pengembangan teknologi masa depan, memungkinkan Indonesia bersaing dengan sistem artificial intelligence global. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun juga menjadi pusat riset kegempaan, pemetaan sesar, tsunami, gerakan tanah, serta kajian risiko dan resiliensi bencana untuk mengurangi dampak bencana geologis. Selain itu, riset iklim dan atmosfer yang dilakukan mendukung mitigasi bencana alam, pengelolaan lingkungan, dan pencapaian tujuan pembangunan berkelanjutan. Fasilitas pengujian untuk memastikan bahwa teknologi dan produk baru memenuhi standar kualitas dan keandalan yang tinggi. Di kawasan ini, tempat di mana ide-ide baru lahir. Kolaborasi antara periset, industri, dan mitra internasional menciptakan solusi inovatif yang berdampak luas. Selain itu, kawasan ini dilengkapi dengan co-working space yang dirancang untuk menciptakan lingkungan kerja yang produktif dan kolaboratif bagi sivitas BRIN dan para kolaborator. Fasilitas di kawasan ini telah memenuhi standar pelayanan publik, mencakup tempat ibadah, parkiran, dan toilet khusus disabilitas, tempat menyusui dan daycare, kafe, serta fasilitas kebugaran baik di luar maupun di dalam ruangan. Kami juga menyelenggarakan seminar, workshop, dan pelatihan untuk meningkatkan keterampilan para periset dan SDM pendukung riset, serta berbagi pengetahuan terbaru dengan masyarakat. Kawasan Sains dan Teknologi Samaun Samadikun Bandung adalah salah satu bentuk komitmen BRIN untuk memajukan ilmu pengetahuan dan teknologi di Indonesia. Dengan fasilitas modern dan aktivitas riset yang beragam, kami bertekad untuk menciptakan dampak positif melalui inovasi. Bergabunglah bersama kami dalam merancang masa depan yang lebih baik melalui riset dan teknologi. Kawasan Sains dan Teknologi Samaun Samadikun Bandung, di mana ilmu pengetahuan dan inovasi bertemu.
Research Center for Electronics is part of the Research Organization for Electronics and Informatics at BRIN. The Research Center for Electronics, or RCE, is home to 8 research groups that work together to explore new ideas, develop innovative tools, and contribute to national development through electronic science and technology. Advanced Photovoltaic and Functional Electronic Devices Research Group is one of the research groups in RCE, which specifically focus on the development of photovoltaic and functional electronic devices technology using novel semiconductor materials and the optimization of their fabrication process to obtain highly efficient devices. The objectives of this team are: 1. To bring together a multidisciplinary research team. 2. To be the center of excellence for research and innovation in the field of advanced photovoltaic and functional electronic devices technology. 3. To achieve a combined balance between high-quality science and practical technology as the main research output. This research group is located in KST Samaun Samadikun, Cisitu, Bandung, Indonesia, which is known to be the home of Advanced Semiconductor Device Fabrication Center. At BRIN KST Samaun Samadikun Bandung, a wide range of state-of-the-art photovoltaic device fabrication and characterization facilities are available to support the research and development activities. Together, we aim to build technologies that are not only advanced, but also meaningful and impactful. Electronics is a key area of science and technology that supports many aspects of modern life. In this research group, we believe that the development of advanced photovoltaic and functional electronic devices are essential as the building blocks for determining innovative electronics technology in the future. We also believe that collaboration is central to our work. Therefore, any future collaborations are always welcomed.
Dye-sensitized solar cell is one of the newest third-generation solar cell technology. Just like photosynthesis in plants, DSSC uses dye molecules to absorb light and then convert them into electricity through photoelectrochemistry. The key benefits of DSSC modules are clean and sustainable. The DSSC in this innovation runs on solar energy, which provides clean, endless power since it is the most abundant source of energy in the universe. So you will never run out of energy as you can charge anytime, anywhere, wherever there is light. Affordable. DSSC module uses much cheaper materials than the conventional crystalline silicon-based solar panels. DSSC can also be produced using simple processes in a typical lab without the need of high vacuum equipment. Flexibility. Unlike conventional PV, DSSC not only works under direct sunlight but also works under artificial light indoors and even on cloudy days. It can also be made in various sizes, colors, transparent, and even flexible. Integration. DSSC can be applied in building integrated PV, providing energy in smart buildings, yet with an aesthetic visual. It can also be integrated into IoT and electronic devices and various smart gadgets in your daily life. The integration opportunities for DSSC are endless. DSSC, a device that charges with light, not only better for you, but also for the environment.
peserta riset asisten di sini. Dan yang saya sekarang diteliti, yang meneliti nanti tentang sel surya. Ayo kita sambil jalan. Jadi sel surya, karena kita hidup di negara yang lebih tropis yang memiliki matahari 12 jam, jadi kita harus meneliti mengenai sel surya atau device yang dapat menghasilkan energi listrik dari cahaya matahari. Nah, yang kebetulan untuk saya sendiri itu riset tentang material dari si sel surya tersebut, yaitu material perovskite. Tapi lebih spesifiknya itu menggunakan inorganic perovskite solar cell. Yuk, aku biar tahu cara bikin solar cell.
Step pertama adalah untuk mengambil prekursor dari glove box dengan hati-hati karena prekursornya sangat rentan terhadap oksigen, sehingga harus di-store di dalam glove box sehingga diambil. Nah, setelah diambil, step berikutnya adalah untuk mendeposisi prekursor kepada substrat sehingga menghasilkan lapisan-lapisan sel surya tersebut. Dideposisikan menggunakan spin coater. Untuk caranya adalah untuk meneteskan beberapa tetes dalam substrat kemudian di-spin sehingga menghasilkan sebuah lapisan tipis. Kemudian lapisan-lapisan berikutnya dideposisi dan juga dipanaskan di atas hot plate untuk membentuk film tipisnya. Step terakhir adalah mendeposisikan lapisan kontak, yaitu menggunakan karbon, sehingga akhirnya terbentuk sel surya yang nanti akan diuji dengan menggunakan solar simulator.
Gimana kalian semua setelah melihat ini? Apakah tertarik mengikuti program Research Assistant? Jika tertarik, klik di bawah sini. Dan kalian bisa mendapatkan banyak ilmu dan pengalaman dari periset-periset di BRIN.
Kawasan Sains dan Teknologi Samaun Samadikun Bandung, sebuah pusat inovasi dan riset unggulan di Indonesia. Di sini, masa depan ilmu pengetahuan dan teknologi dirancang dan dikembangkan melalui fasilitas mutakhir dan aktivitas riset yang beragam. Di kawasan ini terletak laboratorium riset terpadu kami, tempat di mana periset dari berbagai disiplin ilmu bekerja sama untuk memecahkan tantangan kompleks. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun dilengkapi peralatan canggih yang mendukung riset dalam bidang informasi, komunikasi dan teknologi cerdas, memperkuat sektor transportasi dan teknologi lainnya. Riset kecerdasan buatan, mekatronika dan elektronika di sini mendasari pengembangan teknologi masa depan, memungkinkan Indonesia bersaing dengan sistem artificial intelligence global. Laboratorium di kawasan Sains dan Teknologi Samaun Samadikun juga menjadi pusat riset kegempaan, pemetaan sesar, tsunami, gerakan tanah, serta kajian risiko dan resiliensi bencana untuk mengurangi dampak bencana geologis. Selain itu, riset iklim dan atmosfer yang dilakukan mendukung mitigasi bencana alam, pengelolaan lingkungan, dan pencapaian tujuan pembangunan berkelanjutan. Fasilitas pengujian untuk memastikan bahwa teknologi dan produk baru memenuhi standar kualitas dan keandalan yang tinggi. Di kawasan ini, tempat di mana ide-ide baru lahir. Kolaborasi antara periset, industri, dan mitra internasional menciptakan solusi inovatif yang berdampak luas. Selain itu, kawasan ini dilengkapi dengan coworking space yang dirancang untuk menciptakan lingkungan kerja yang produktif dan kolaboratif bagi sivitas BRIN dan para kolaborator. Fasilitas di kawasan ini telah memenuhi standar pelayanan publik, mencakup tempat ibadah, parkiran, dan toilet khusus disabilitas, tempat menyusui dan daycare, kafe, serta fasilitas kebugaran baik di luar maupun di dalam ruangan. Kami juga menyelenggarakan seminar, workshop, dan pelatihan untuk meningkatkan keterampilan para periset dan SDM pendukung riset, serta berbagi pengetahuan terbaru dengan masyarakat. Kawasan Sains dan Teknologi Samaun Samadikun Bandung adalah salah satu bentuk komitmen BRIN untuk memajukan ilmu pengetahuan dan teknologi di Indonesia. Dengan fasilitas modern dan aktivitas riset yang beragam, kami bertekad untuk menciptakan dampak positif melalui inovasi. Bergabunglah bersama kami dalam merancang masa depan yang lebih baik melalui riset dan teknologi. Kawasan Sains dan Teknologi Samaun Samadikun Bandung, di mana ilmu pengetahuan dan inovasi bertemu.
Research Center for Electronics is part of the research organization for electronics and informatics at BRIN. The Research Center for Electronics, or RCE, is home to 8 research groups that work together to explore new ideas on the development of photovoltaic process to obtain
sebuah pusat inovasi dan riset unggul pusat inovasi dan riset unggulan di Indonesia. Di sini masa depan ilmu pengetahuan dan teknologi dirancang dan dikembangkan melalui fasilitas mutakhir dan aktivitas riset yang beragam. Di kawasan ini terletak laboratorium riset terpadu kami, tempat di mana periset dari berbagai disiplin ilmu bekerja sama untuk memecahkan tantangan kompleks. Laboratorium di kawasan Sains dan Teknologi Samangun Samadikun dilengkapi peralatan canggih yang mendukung riset dalam bidang informasi, komunikasi dan teknologi cerdas, memperkuat sektor transportasi dan teknologi lainnya. Riset kecerdasan buatan, mekatronika dan elektronika di sini mendasari pengembangan teknologi masa depan, memungkinkan Indonesia bersaing dengan sistem artificial intelligence global. Pengujian risiko dan riset iklim dan atmosfer yang dilakukan pengujian untuk memastikan yang berdampak luas. Dilengkapi dengan coworking space yang dirancang untuk menciptakan lingkungan kerja yang produktif, BRIN, dan para kolaborator. Fasilitas di kawasan ini telah memenuhi standar pelayanan publik, mencakup tempat ibadah, parkiran, dan toilet khusus disabilitas, tempat menyusui dan daycare, kafe, serta fasilitas kebugaran baik di luar maupun di dalam ruangan. Kami juga menyelenggarakan seminar, workshop, dan pelatihan untuk meningkatkan keterampilan para periset dan SDM pendukung riset, serta berbagi pengetahuan terbaru dengan masyarakat. Kawasan Sains dan Teknologi Samangun Samadikun Bandung adalah salah satu bentuk komitmen BRIN untuk memajukan ilmu pengetahuan dan teknologi di Indonesia. Dengan fasilitas modern dan aktivitas riset yang beragam, kami bertekad untuk menciptakan dampak positif melalui inovasi. Bergabunglah bersama kami dalam merancang masa depan yang lebih baik melalui riset dan teknologi. Kawasan Sains dan Teknologi Samangun Samadikun Bandung, di mana ilmu pengetahuan dan inovasi bertemu.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. I'm Nunik Nurhayati, a researcher at the Research Center for Electronics, National Research and Innovation Agency of Indonesia. We are now in the final session of the second Symposium on Advanced Photovoltaics 2025, and I will be serving as the session chair for this session. In this session, we have three presenters from the young scientists who will share their research, as well as a keynote address from a distinguished speaker. Before we begin the young scientist presentation, let me introduce the three young scientists who will be presenting. The first one, we have Mr. Ihsanul Mubarak from Universitas Pajajaran. The second one, we have Dini Setiani, Master of Science from Universitas Gadjah Mada. And the third one, we have Photovoltaic, Master of Science from Institut Teknologi Bandung. Welcome. In this young scientist session, the total time for the presentation and Q&A session for each presenter is 15 minutes, with 10 minutes allocated for the presentation and 5 minutes for Q&A. Let's begin with the first presenter, Mr. Ihsanul Mubarak. Are you there?
Yeah, I'm here.
Okay. Mr.
Oh,
Ihsanul Mubarak, the screen is yours, so you can start your presentation.
okay, sorry, I moved to better place. Okay. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Yeah, good afternoon, everyone, distinguished speakers and participants. It's an honor to be here today. My name is Ihsanul Mubarak. I am from the Department of Physics, Universitas Pajajaran. And today I will present my work entitled Water-Based Cesium Lead Bromide Perovskites Solar Cells. Okay, next slide, please. This is the outline of my presentation. I will start with the background, research objective, research method, the result, and then optimization attempts, comparison, and significance, and finally the conclusion. Next. Okay. Perovskite solar cells are highly promising due to their rapidly increasing efficiency. However, hybrid perovskites such as methylammonium lead iodide degrade rapidly under moisture and oxygen exposure. Next. Yeah, in contrast, inorganic perovskites such as cesium lead bromide exhibit higher stability, making them suitable candidates for long-term applications. Next. Fabrication of cesium lead bromide typically relies on toxic solvents such as DMF or DMSO, which are harmful to both health and the environment. Several studies have attempted to replace cesium bromide solvents with water, but lead bromide is still mostly dissolved in toxic solvent. Ding et al. Demonstrated that lead bromide can be dissolved in SPR S2O with PAG, producing homogeneous films. However, their study did not clarify the fabrication environment or humidity tolerance. Next. In this study, we fabricated cesium lead bromide perovskite solar cells using a two-step spin coating method. Lead bromide was dissolved in SBR and water with addition of PAG with concentration of 5%, 7%, 10%, and 12%. The cesium bromide was dissolved in water, and all fabrication was performed under ambient air with high humidity above 70%. The device structure was glass FTO and titanium oxide as blocking layer, as mesoporous titanium oxide, cesium lead bromide perovskites, carbon, and silver. Yeah. Next. The objective of this research were to produce homogeneous void-free cesium lead bromide perovskite films, to analyze the effect of PAG concentration on UV-Vis absorbance, crystal structure, and morphology of cesium lead bromide thin films, and to analyze the effect of PAG concentration in lead bromide solvent on the performance of cesium lead bromide perovskite solar cells. Next, yeah. In this study, the perovskite solar cell fabrication process follows this flow diagram. The perovskite layer coated using two-step spin coating technique, and the other layers coated using screen printing technique. The substrate used is FTO glass that has been coated with titanium oxide, as shown in this figure. Next. For the result, here are shown the XRD characterization result of two samples. XRD results show distinct differences between films without PAG and those with PAG addition. For film without PAG additions, contain cesium-rich secondary phases such as tetracesium lead hexabromide, indicating incomplete reaction. The average crystallite size for this sample was 27.8 nanometer. For 10% film, for film with 10% PAG, showed nearly pure cesium lead bromide with reduced secondary phases and a larger crystallite size of 46.2 nanometer. This demonstrates that PAG facilitated more complete crystallization and improved film quality. Next. Yeah. From the UV-Vis absorbance spectra, indicated a strong absorption between 520 until 530 nanometer for all samples. Film with 10% PAG exhibited the highest absorbance intensity, suggesting enhanced light harvesting capability. Next. Yeah. Tau plot analysis showed band gap energies ranging from 2.25 to 2.31 electron volt. The lowest band gap was obtained with 10% PAG, enabling better photon absorption. These findings confirm that PAG not only affect morphology but also directly impacts the optical properties crucial for solar cell performance. Next. SEM image are shown here. Highlighted clear differences. For film without PAG has non-uniform surfaces, rough texture, and visible voids, indicating poor crystal connectivity. Film with 10% PAG has smoother and more compact morphology with better grain distribution. These improvements in morphology explain the enhanced charge transport and reduced recombination observed in electrical measurement. Next. The performance of the perovskite solar cells device is measured using current voltage measurement. Current voltage measurement under illumination revealed that the best performance was obtained with 10% PAG, achieving a VCE of 3.14% with short circuit current of 5.863 milliampere per centimeter square, for open circuit voltage of 1.0 one for 7-fold and fill factor of 0.467. Interestingly, the highest GSE was observed in the 7% PAG sample, but other parameters were less optimal, resulting in lower efficiency. Next. Yeah. Further optimization was conducted by varying the spin coating speed following the work of Mehdi et al., who reported significant effects of spin speed on film quality. Next. Three spin speed were tested: 2,500, 3,500, and 5,000. But yeah, the results were not as expected. The best performance was still obtained at 3,500 RPM with PCE of 3.14%. Next.
Mr. Isanul, sorry,
Yeah.
you have 1 minute left for presentation.
Okay, the second optimization involved varying the cesium bromide loading time based on U et al., who showed that loading time could influence film quality into step spin coating. Next. In this study, loading times is 15 seconds and 30 seconds were tested. However, both resulted in poorer performance compared to the baseline, which is without loading time. The best result remained at 3,500 RPM without additional loading time. These results emphasize that both spin speed and loading time are critical parameters, and that optimized PAG concentrations play a larger role in device quality. Yeah, although the efficiency in this study is lower than that reported by Ding, there are two key contributions. First, successful fabrication of cesium lead bromide perovskites solar cells using fully water-based solvent under high humidity ambient conditions. And second, the active layer area in this study was 0.24 centimeter square, 6 times larger than Ding's device, showing scalability potential. In conclusion, water-based solvent with PAG successfully produced homogeneous and fine-free cesium lead bromide using a two-step spin coating technique. PAG concentration significantly influenced the morphology, crystallinity, and optical absorption, with 10% PAG being optimal. And the addition of PAG significantly impact the performance of peroxide solar cells, with 10% PAG concentration result in the highest power conversion efficiency of 3.14%. Thank you very much for your attention. I hope you found this information useful. At this point, I will return it back over to the moderator. Thanks.
Okay, thank you, Mr. Isanul, for the nice presentation. To the audience, if you have any question, you can raise your hand or write down on the chat box. Okay, we have one question from Dr. Wilman. You can ask directly.
Okay, thank you. Thank you, Mr. Isanul. It's very interesting work. So it's very interesting. Do you use only water as the solvent for the lead bromide? Because as far as I know, has very low solubility. So is the addition of the hydrogen bromide in your case has the role to dissolve this lead bromide? Yeah, that's my question. Thank you.
Okay, you can answer directly.
Okay. Thanks, Mr. Wilman, for the questions. Yeah. For the solvent we used in the study, for lead bromide solvent, we use SBR solutions, yeah, I think it's the role of SBR, it makes lead bromide what what
Yeah,
sorry.
how much you add the
yeah.
bromic acid, the HBr? How much? I mean, is the solution very acidic?
Yeah,
I'm just wondering how you can get. Is it clear solution at the end, or how is it?
Yeah, we use 40% SBR solutions. Yeah, it's very acidic, and the lead bromide solution is very clear. We very transparent, and it's very has very nice solubility. Sorry.
Maybe a little bit. How much is the concentration of the lead bromide?
47%.
The molarity. I mean,
sorry.
the molar.
The molarity. Sorry. Sorry. No.
1 molar.
I mix the 0.782 gram for 1 milliliter SBR solution.
Yeah. I see. Maybe around 1 molar. Okay. Thank you very much.
Yeah.
Okay.
Yeah.
Thank you for the question, Dr. Yoman, and also for the answer. I think we have a limited time, so as we have reached 15 minutes, let me draw a little conclusion. Introducing toxic solvents, the addition of polyethylene glycol has a significant impact on the performance of the perovskite solar cells. 10% polyethylene glycol concentration resulted in the highest power conversion efficiency. Okay, I would like to say thank you to Mr. Isanul, and please give applause. And let's proceed to the second presenter. In the second presenter, we have Dini Setiani, Master of Science. Miss Dini, are you there?
Yes.
Okay, the screen is yours.
Thank you, Dr. Nuni. Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. I'm Dini Setiani from Gadjah Mada University. Today, I will present my study on TiO2 CSPB-BA3 films using spectroscopic ellipsometry. And in this work, I investigate interfacial charge transport and optical dielectric properties, showing that TiO2 concentration strongly affect electron transfer and interfacial behavior. Next. This study is motivated by the growing global demand for energy and the urgent need for renewable solutions. Among them, solar energy is one of the most promising options, as it can be converted into electricity through photovoltaic systems. The development of solar cells is divided into 3 generations. First, silicon-based cells, second, thin films technologies, and the third, emerging concepts such as organic, DSSC, and perovskite solar cells. And perovskite materials, especially MAPBI3 and FAPBI3, have gained attention for their excellent light absorption and high efficiency. However, organic-based perovskites suffer from poor stability. To overcome this issue, inorganic cesium-based perovskite, particularly CSPB-BA3, are considered more stable at room temperature and are a strong candidate for the third generation solar cells. And for efficient operations, a suitable electron transport layer is essential. Titanium dioxide, or TiO2, is widely used due to its high electromobility, stability, and low cost. Next. Nevertheless, most studies remain focused on improving device efficiency. while limited attention has been given to exploring the relationship between electron-hole states and charge extractions mechanisms, which directly impact efficiency. The energy level diagram in the figure highlight the importance of proper energy alignment between materials for effective charge transfer. Specifically, CSP-BBR3 and TiO2 exhibit favorable energy matching, where the work functions of CSP-BBR3 lower than that of TiO2, thereby facilitating electron transfer. To gain deeper insight, optical characterization is required. In this work, we employ spectroscopic calypsometry to investigate charge transfer between the CSP-BBR3 and TiO2 and to analyze the effect of TiO2 concentration on electron generation. Next. In this work, we use CSBR, PBBR2, DMF, titanium disopropoxide, ethanol, deionized water, and quartz substrate. And the fabrication began with the deposition TiO2 layer on quartz using spin coating, followed by the annealing. And the precursor solution was prepared in 3 concentration, 0.15 and 0.30.5 molar. After the TiO2 layer was formed, we fabricated the CSP-BBR3 film using a spin coating method, followed by the annealing. And first, a PBBR2 layer was deposited and annulled, and then the CSPR was applied by spin coating and subsequently annulled to complete the formation of the perovskite layer. Next. For the characterization, we use XRD to analyze the crystal structure and SEM to observe the morphology. And to study the optical properties, we perform spectroscopy ellipsometry, which is based on the principle of polarized light reflection. And each layer was then fitted with different optical models using Fresnel analysis to extract key parameters such as the dielectric function and optical conductivity. We use a Cauchy model for quartz, the Drew tolerance model for CSP-BBR3 and TiO2, and the Bragman for effective medium approximation. Next. This SEM image show the morphology of pristine and TiO2 CSP-BBR3 films. So the pristine is uniform but contains large pinholes, and the 0.15 molar TiO2, the film remains uniform, but the grain size increases slightly and the pinholes become smaller. And at 0.3 molar TiO2, the film shows the best quality with uniform coverage and the grain size around 943 nanometers and fewer pinholes. And at 0.5 molar, the morphology changes to a cubic structure, the grain size decreases significantly and many pinholes reappear. Next. And this slide shows the XRD patterns of pristine and TiO2 CSP-BBR3 films. The diffraction peaks confirm the orthorhombic path of CSP-BBR3 and the NATS path of TiO2, while the perovskite structure remains preserved and the FWHM values are nearly identical, which is indicating that the crystallite size is not significantly affected by a TiO2 layer. Next. Here we show the fitting results of C and delta for CSP-BBR3 pristine and TiO2 CSP-BBR3 films. The experimental and the model match well, and the mean square error values are below 1, confirming a good consistency across all samples. Next. And here show the complex dielectric function of TiO2 CSP-BBR3 films. In a figure 3.4a, show that the addition of TiO2 improved the optical properties compared to pristine. As the TiO2 concentration increased, the real part epsilon1 gradually decreases. And in figure 3.4b, we can see the 3 main optical transition. The first transition E1 occurs at the gamma point with an energy about 2.36 eV. The second transition E2 appears the R point around 3.7 eV, and E3 near 5 eV correspond to the valence to conduction band transition at U point. Next. And this slide shows the optical conductivity. In figure 3.58, spectrum is divided into three regions, R1, R2, R3, shown in the table 1 for the energy range. And then for the sigma 1, increase with the TiO2 concentration except at 0.5 molar in R1. And in figure 3.5p, delta sigma 1 is positive for 0.15 and 0.3 molar, indicating active optical interactions, but becomes negative at 0.5 molar, showing electron transfer from CSPBBR3 to TiO2. Next. In this slide show in figure 3.6a, the highest spectral weight appears at 0.15 molar TiO2 across the full energy range, but decreases at 0.3 and 0.5 molar. And then the figure 3.6b show a similar trend for partial spectral weight, increasing up to 0.15 molar, then dropping in all regions. This suggests that moderate TiO2 enhance the optical response, while excess reduce efficiency due to saturation. Next. In this slide, illustrate the spectral weight and density of state. The TOS diagram at the top show the occupied state dominated by Br4p orbitals in the valence band and the unoccupied states involving Pb6p orbitals in the conduction band. At 0.15 molar TiO2, the TOS of CSPBBR3 increases because electrons excited in TiO2 transfer to the CSPBBR3 conduction band, enhancing carrier density. In contrast, at 0.5 molar, the TOS decreases as electrons back transfer from CSPBBR3 to TiO2, reducing the available states. Next. In conclusions, TiO2 serves as an effective electron transport layer that regulates charge transfer in the TiO2 CSPBBR3 systems. The 0.15 concentration is the most favorable, as it enables efficient electron transfer into CSPBBR3, enhancing the density of states and conduction band optical states with minimal resistance. However, at 0.5 molar, the charge transfer become less efficient due to electron back transfer into TiO2, creating energy barriers and increasing recombination at the interface. Next. Okay, thank you very much for your attention. That concludes my presentation. I now return the session to moderator.
Okay, thank you, Ms. Dini, for the presentation. Nice presentation. Now we have a question, I think, from Ms. Rosaila. Ms. Rosaila, so you can ask directly, and Ms. Dini, you can kindly answer the question directly. Okay.
Okay, thank you, Dr. Nunik. Can you hear my voice? Okay. Thanks, Ms. Dini, for the presentation. That was an interesting topic. So, according to your presentation, in your band structure analysis, you mentioned there is a transition of the K points R and U that was 5 electron volt and I think around 3.5 electron volt. Could you please elaborate how is the optical properties? Because somehow in the paper, I think it's only like closer K points. Yeah.
Okay, can I answer?
Okay, yes, you can answer directly.
The correlation is the peaks at E1, E2, E3 correspond to optical transitions because they reflect interband excitations between the valence band and the conduction band at specific key points. At E1, around 2.3 eV, the transition originates from the valence band maximum to the conduction band minimum at gamma point, which is the fundamental band gap of CSP-BBR3. And at E2, near 3.7 eV, the peak corresponds to transition at the R point, where the band structure shows a strong overlap between occupied BR4P states and unoccupied PB and PB6P states, and at E3 around 5 eV is attributed to a deeper valence to conduction transitions at the U point, consistent with the density of states and orbital hybridization. So the dielectric peaks directly map onto interband transitions predicted by the band structure and project dose.
Okay, maybe if you are still curious about this discussion, so you can ask again in the chat box. Okay, I hope I
Okay.
hope the answer can
Thank
answer
you.
can
Dr.
answer
Nami,
the question. Yeah.
yeah,
Okay.
actually, I have one more question.
Sorry, maybe because we have limited time, if you have still any question, you can write on the chat box, and then Miss Dini, please kindly ask the answer also in the chat box. Maybe we have still 1 minute, so there is one question in the chat box. Can you elaborate perhaps how to derive the density of state from ellipsometry measurements, and also on how you draw conclusion about the charge transfer between CSP-BBR3 and TiO2? Okay.
Because so from the ellipsometry result, we get the C and delta, and so I use the fitting models, and finally for the fitting model, I get the dielectric dielectric functions, and then for the dielectric function epsilon 1 and epsilon 2, the epsilon 2 is correspond to the DOS projects. Then we can see the interband transition.
Okay, thank you for the answers. And yeah, we have still some questions. Maybe you, Ms. Dini, I kindly ask you to answer the question in the chat box, and because we have limited time, so we will end this session. For we will continue to other presenter, and please give applause to Ms. Dini. Thank you for your nice presentation. Okay, and for the third presenter, now it's time for the third presenter. In the third presenter, we have Photovoltaic Master of Science, yeah, Mr. Steki. Are you there? Okay, I can see you. So you can share your slide. Okay, and the screen is yours.
That's my slide. Can you see my slide?
Okay, I can see your slide, but you can show the slideshow.
I already show my slide.
Okay.
Okay, thanks. This is clear.
Okay,
Hello?
you can start. Okay, you can start.
Okay. Okay, thank you very much. Good afternoon, everyone. My name is Photovoltaic, and I'm now a doctoral student in chemistry and in division of inorganic and physical chemistry, Faculty of Mathematics and Natural Sciences in Institut Teknologi Bandung. And I'm excited to share part of my research on the investigation on polyethylene oxide composition in iodide redox coupled electrolyte for enhanced dye-sensitized solar cell performance. I want to start my presentation by showing humanity's top 10 problem for next 50 years that proposed by a Nobel laureate, Prof. Smalley. And as we all know, one of the biggest challenges humanity faces over the next 50 years is the energy. With our global population projected to reach 10 billion by 2050, the need for clean, renewable energy sources is more urgent than ever. So, solar energy stands out as a powerful solution to meet this growing demand. This chart from an RER shows the incredible progress in solar cell efficiencies over the years. While technologies like silicon and perovskites have reached high efficiencies, there's a vital category of emerging PV, which you can see here. Within this category are the dye-sensitized solar cell, or DSRC, the focus of my research, which offer unique advantages like low cost manufacturing and good performance in various light conditions. So how does the SSC work? In simple terms, like the dye will absorb the light, which excites an electron. This electron is injected into a semiconductor like titanium dioxide and travels through an external circuit, creating electricity. The crucial part of my research is the electrolyte part, which contains a redox couple like iodide, triiodide. Its job is to donate an electron back to the dye, regenerating it so the cycle can begin again. The efficiency of this charge transport is key to the cell's overall performance. However, traditional DSSCs face a major challenge. They use a liquid electrolyte which can leak and evaporate over time, significantly reducing the long-term stability of the device. Our solution is to transform this liquid into a quasi-solid by adding a polymer. This approach can prevent leakage and reduce evaporation, leading to much more stable and durable devices, and even opening the door for a flexible application. Here's how we did it. We created a series of electrolytes using acetonitril, lithium iodide, and iodine, and then we added the polymer polyethylene oxide, or PEO. We varied the PEO composition from 0%, which is the pure liquid, up to 10% by weight. We then assemble this into the DSSCs and characterize them using several techniques, including FTIR and Raman spectroscopy, electrochemical impedance spectroscopy, and of course, measure their performance under a solar simulator. Photoanode that we use is using FTO, P25 and 719 for the dye. And as the control electrode, we use graphite sheet and funny graphite. And the samples name Ali PX, where the X is the PO weight percent. So I'll call the Ali P0 for the pure liquid until the Ali P10 for 10% of PO added. So first, we look at the electrolyte photo showing here. The viscosity of the electrolyte increase as the PO composition increase, as we can see in the figure. In the molecular level, FTIR and Raman spectroscopy confirm that the PO is interacting with the ions in the electrolyte. For example, if you look at the graph on the left, we can see that there is that actually come from the acetonitril. In the LVP0, it's a big acetonitril. But you can click on the FF number of 842 and 1098. There are CH2 rocking bending in the PO, and the PO is stretching in the PO in the 1098. Also in the Raman, we can focus in the Raman shift around 100 that the peaks belong to the triiodide vibration. So we can see as increasing the PO composition, we can see there is more flexible TH2 rocking bending. It's shown by the LEP5 sample. And the more rigid COC stretching is also given by the LEP5. What it means, we can imagine that the COC stretching is the backbone of the polymer. So it should be, the more rigid it will be better. So the backbone of the polymer is not move much, but the CH2 rocking is very flexible, so it can interact with the triiodide. So the triiodide can do some hopping mechanism to transfer the electron. And we can see also in the Raman, the triiodide bending is more flexible in the LEP5 also, so it can transfer the charge through the hopping mechanism. So next, we ask, how do these molecular changes affect the movement of ions? We use the EIS to find out. This Nyquist plot shows the impedance of the cell. The key takeaway is on the right, where we plot the ionic conductivity. As we add the PEO, the conductivity changes, with the highest value seen in the 5% and 7.5%. This indicates there's an optimal amount of PO for efficient ion transport that I tell you about the mechanism before, the hopping mechanism. So we also use Bode phase plots for our EIS data to calculate the electron lifetime, or the time constant of this electron. This is important because a longer lifetime means less unwanted charge recombination. We found that the sample with 5% PO or LEP5 showed the longest electron lifetime of over 50 microseconds, suggesting it's the most effective at preventing the recombination. So this all leads to the most important question. What is the final performance of the solar cell? Here are the JP curve. As you can see from the table, the cell with 5% of PO labeled LEP5 achieve the highest power conversion efficiency of the quasi-solid cells at around 2.15%. It's near the liquid LEP0, around 2.16%. It produced the highest short circuit current at 5.75 milliampere per centimeter square and a high open circuit voltage of 0.58 volt. So we can see among the other quasi-solid cells, the LEP5 give us the best performance. So what is to summarize my key findings? First, we confirm with the spectroscopy that PO directly interacts with the redox couple, creating a more flexible structure for ion movement, especially at 5% of PO. The second one is EIS show that adding PO successfully created a gel and actually increased ionic conductivity at certain concentrations. And finally, we found an optimal concentration of 5% PO, which achieved the best efficiency of 2.15% among the other quasi-solid cells by creating a perfect balance between physical stability and efficient charge transport. Thank you for your attention. I'd be happy to answer any question. Thank you.
Okay, thank you so much, Mr. Steki, for the nice presentation. Now it's time for the Q&A session. So to the audience, if you have any questions, you can raise your hand or write down on the chat box. Okay, while waiting for the question from the audience, so I have a question. I have a question about the impedance measurement. In impedance measurement, they are in the graph. The graph shows the two RCT data, RCT1 and RCT2, charge transfer resistant 1 and charge transfer resistant 2. So what does RCT corresponds to?
Oh, okay. Thank you. The RCT, we use equivalent circuit like RS and then RCT1 with the CPE1. And this RCT1 is corresponding to the electron transport from the counter electrode. So from the counter electrode into the electrolyte. And the CPE is how it act like the capacitor light. So the LCT2 is the electron transport happening in the photoanode. So from the titanium dioxide and the dye, transport electron to the electrolyte. And it's also act like a capacitor light. That's why we added also the CPE2 there.
Okay,
That's
thank you
what
for
the LCT is corresponding for.
okay, thank you for the answer. So we have question. We have question from Mr. Yuda Prima. You can ask directly to Mr. Steki. Okay.
Okay, thank you so much, Mr. Steki, for the nice presentation. So basically, I'd like to ask some questions about the same thing about the impedance. So as Dr. Nuni mentioned before, but in this case, for me, I don't have any experience to work on the what do you call DSC or even any type of solar cell because I'm working on battery. But at least I would like
Okay.
to know. Maybe later on I can work on it. So for the measurement of this impedance, so did you measure it by three electrode system or by direct a full cell system? That is the first questions. And the second question is, in the border plot, you show about recombination time, right? Recombination time that you can correlate to the peak from in which the frequency we can take it. So basically, from this, I mean interpretation. So this recombination time is the recombination time that occur in which process, because basically for my understanding, DSSC maybe, there are a lot of jumping for the electron. So maybe the electron can go from the, the LUMO of the DSC to the TiO2 and something like that. So maybe you can elaborate for this explanation. Thank you so much, Mr. Steck.
Okay. Thank you, Mr. Yuda. Can I answer directly?
Okay, you can answer directly.
Okay. The first question is about excuse me, I little forget about it. What is the first question?
Sorry?
The first question is
Oh, yeah, the first question is about, did you measure it? Sorry, there is
oh yeah,
aircraft.
the
So
three electrode or something.
okay, so yes, is there how did you measure this impedance measurement? So did you measure
Yeah.
it by three electrode system or by full cell system?
Okay. Thank you. Actually, we use the a full cell system. So I made a full cells like there is a photoanode electrode and a contact electrode. So and I measure the impedance using the Hioki LCR method using I think it's for electrode, the two electrode in the working electrode and two electrode in the contact electrode. That is how I measure it. I hope it's answer your question. And the second question is, yeah, I show the body plots here and the electron lifetime I get from the peaks here in around like maybe in log frequency 3 to 4. I use the equation 1 per 2p times the frequency. So I believe in this peaks, it's some mixed electron charge transfer between the electron transfer in the contact electrode and in the photoanode. In the normal DSSC cell, they use a platina in the contact electrode. And if we use the platina, it will separate into the two peaks The first peak is the electron transfer in the photoanode to electrolyte, and electrolyte, and the other one is the from control electrode PT base to the electrolyte. But in my condition, because the control electrode is using some graphite sheet that we screen printed the composite of tiny graphite there. So it's the charge transfer of electron. It's similar between the photoanode and the contact electrode. So that's why I believe this peaks is the mixing between two of them. So it's just become one peak, but actually it's two peaks there actually. That's what I believe. But I didn't fit it yet. Yeah, it's nice. I will do it later, I think, to make it clear. That's
Okay.
Mr. Yuda.
Okay. Due to the limited time, but we still have questions. So due to the limited time, so you can answer the question in the chat box. We have the question in the chat box, and you can ask, you can answer in the chat box. Now, I think the young scientist session is over. So next we will move to the another part of the session. So thank you, Mr. Steki, and please give applause. Okay, now we have a keynote speaker, Dr. Muhammad Naufal Lintang Pradipto. Dr. Muhammad Naufal, are you there? Okay, still unmute, maybe. Okay. Okay.
Yes, I'm here. I can
Okay.
listen.
Okay. Let me introduce him briefly. Dr. Muhammad Naufal finished his bachelor's degree at Institut Teknologi Bandung, his master's degree at Korea Advanced Institute of Science and Technology, Korea, and his doctoral degree at King Abdullah University of Science and Technology, Saudi Arabia. He is currently a postdoctoral researcher at the Institute for Photovoltaic, University of Stuttgart, Germany. In this session, he will talk about single crystal perovskites, unlocking the next generation of solar cells efficiency. The total time for the presentation and Q&A session is 45 minutes, with 30 minutes allocated for the presentation and 15 minutes for the Q&A. Okay, Dr. Muhammad Lintang, the screen is yours.
Thank you. Thank you. Should I share my screen now?
Okay, you can share your slide.
Can you see, guys, my screen?
I can see, but I think you need to do a slideshow. Okay.
Yeah, how about
That's
now?
okay. Yes, now it's okay. You can start.
Okay, good afternoon, everyone, distinguished speaker, college, and members of scientific community. It is truly an honor for me to be here at the second Symposium in Advanced Photovoltaic 2025, organized by BRIN, National Research and Innovation Agency, to share some of my recent progress in the field of perovskite solar cells. As the host already mentioned, my name is Muhammad Naufal Lintang Pradipto. I'm a postdoctoral researcher in University of Stuttgart, mainly in Institute for Photovoltaic. And today I will present to you my journey with single crystal perovskite solar cells and their potential to unlock the next generation of the solar cell efficiency. And in this talk, I will start by giving you an introduction about a little bit information about perovskite, and then also the differences between the single crystalline and polycrystalline perovskite, and why we have to move on from polycrystalline solar cell of perovskite, and how it is performing now single crystal perovskite solar cells. And later on, we'll be explaining about what's next for single crystal perovskite solar cells. And hopefully it can be recognized soon as the next generation for solar cells perovskites. So now we are going on with the little bit basic information. As I think all of you already know about this, but I'm just going to give you a brief information that perovskite is a structure that has a general chemical formula of ABX3, where the octahedral corner sharing BX6 are located in the corner. And then in the center part, there is organic and inorganic cation. And we can choose many options for perovskite according to this element. So we have three elements, A, B, X3. A, it's mostly organic and inorganic cation. We have many choices such as methyl ammonium, formamidinium, in this case is organic material. For inorganic material, oh, sorry, I will just show this one. Yeah, for the inorganic material, we can choose many of them. One of you is cesium and rubidium. And for the B material, B element in here is a metal cation. We can choose many of them. One of them is lead and iodide. Lead and then tin or strontium, and also titanium. And the X or halide anion can be chosen from the halogen option, which is the chlorine, bromine, iodine. So in this case, we have many options to make a perovskite with the ABX3. With this many diverse option, we can apply perovskite to many applications. Not only they are able to be used in many applications, they are remarkably working well in that region as well. Such as in solar cell, we know we reach around 27% now efficiency from the Suzhou University and UNSW from Sydney. It's a remarkable efficiency in compared to silicon solar cell that in polycrystalline form, they reach 23%, and the silicon heterojunction is about 27.8. So we are in the range of commercialization right now for polycrystalline one. And in the aspect of LED, in our phone, mobile phone, we use OLED, organic LED, that has an EKE for about 40%. And in perovskite, we already show that with the perovskite green LED, we can reach 30% of EKE. And in the laser aspect, with the possibility of color tunability, we can get many choices of laser for perovskite. And if we compare with the 3 to 5 semiconductor that mainly used in optical application now, we have a number of 70% of PLQY, and it's in the same range as a 3 to 5 semiconductor. In X-ray detector, perovskite doesn't need even bias to make it work, and it gives a sensitivity to 10 to 5 microcoulomb gyro, and it's way above the one that we mainly use in healthcare instrument, which is the selenium-based detector. So basically, perovskite has shown many possibilities to use in many advanced applications, and the question comes back to why perovskite can perform well, and it goes to the excellent optoelectronic properties of the perovskite. Tunable band gap, I already mentioned to you that because we changed the halide anion, we changed the element of the ABX3, we can get different band gap. If we want to get a higher band gap, we can use it for water splitting element or water splitting application. If we want to get for solar cell, we just lowering down the band gap to narrow band gap. Or we can tune the location of the band gap for laser, different laser, red, green, and whatsoever. And also for high absorption coefficient, it allows perovskite to absorb the sunlight efficiently with only very thin layer, and this allows them to be a lightweight product for many applications. And their number is in the range number of gallium arsenide and also CIGS, which mainly used now in the rocket space application. And the long diffusion length of perovskite give them the possibility to work on not only thin devices, but also thick devices. And it's possible for certain applications such as the X-ray detector. It allowed them to have a very large charge extraction location from the center part of the exciton generation. Therefore, it is useful for certain applications, likewise with that require certain thickness for absorption, such as X-ray irradiation or gamma irradiation. And additionally, high defect tolerance allow perovskite to be very easy to access, especially to produce. And it's require very small amount of money in compared to the other very complicated process of production. And this high defect tolerance means that when perovskite are produced with the solution, they produce a lot of defect. However, that defect are located in the shaft, in the shallow state location, where when we irradiate the perovskite, we basically return back all the defect states from the shallow location into the original location. So it allowed them, even though with the very high defect condition, to be still perform well as a device with a light irradiation. And then because of the solution process base, perovskite are easily tuned or modified into different shapes or formation, such as 0D, 1D, 2D, and 3D. And these allow them to be used in many applications as well. By modifying or tuning the organic or inorganic cation, in this case, the large organic cation, we change the corner sharing octahedral sheet in here from 3D into the octahedral sheets in 2D, or even octahedral rod in 1D, or even octahedral dots in 0D. And these correspond to the formation of the structural level of nanocrystal or quantum dots, some of them say that, or nanorod or nanosheets on bulk material. But in this case, we're going to focus on the bulk materials of perovskite, which are classified mainly into two categories, which is polycrystalline and single crystal. Now we know polycrystalline and single crystal are the two classified that is mainly taught in perovskite in general. But the big differences of these polycrystalline and single crystal is the presence of the boundary, the grain boundary. As you see from the SEM image in here, we have a grain boundary for the polycrystalline perovskite and no grain at all in the single crystal one. And the grain boundary actually produce such a dangling bond on the every edge of this boundary, and then that dangling bond act as a defect and trap states. And not only that act as a trap state, they also act as a recombination non-radiative states. Therefore, the presence of the grain boundary is actually non-beneficial for perovskite, especially with the presence of the water. They can intercalate and make as a degradation center for perovskite. As we know, we have organic material in the perovskite composition. Therefore, whenever we do stability tests between polycrystalline and single crystal, we always see that single crystal are superior in compared to the polycrystalline, as you see on the right image that we did previously. I summarized a little bit of advantage of single crystal from this table. The perovskite single crystal can stable up to months or even year in compared to the polycrystalline one that can up to days or weeks. And the trap density, thanks to the presence of the grain boundary, the trap density of polycrystalline are much more higher, 10 to 19 compared to single crystal, which is 10 to 12 centimeter minus 3. And the diffusion length for polycrystalline are limited by the grain size of the crystal, which is about 1 micron, and for single crystal are limited by the size of the thickness of the crystal, which is about 500 micrometer. So we know that this advantage is actually to use single crystal as a device. In this case, we are talking about solar cell, but we have to know how to crystallize perovskite first to understand more later when we talk about single crystal perovskite solar cell. So there are several methods to crystallize single crystal of perovskite. The first method is called classical cooling crystallization. It's a method where you put the precursor solution into acid-base solution, where you are trying to reduce the temperature to induce supersaturation condition on the solution. And then by reducing the temperature, you are reaching a condition where you start to nucleate crystal. However, this process takes a time scale of about months to produce such a crystal. So it's not really advantage to use this. A second one is the antisolvent vapor acid crystallization, where you are using a vapor diffusion to induce supersaturation crystallization process. So by having a precursor in certain of solution and then try to use antisolvent where it's miscible to the solvent, but not dissolving the perovskite, it creates a supersaturation condition and it nucleates the crystal. But the time scale for this is about days to weeks. So it's a bit time consuming for the process of crystallization as well. And the last one is the inverse temperature crystallization, where it's developed by my PhD advisor, where they are developing a method in the few hours time scale. By using a polar aprotic solvent, they put the perovskite into a solution and then heating up the solution, and it reaches a supersaturation condition based on the solubility curve, and then they start to nucleate in the hour time scale. There's also another method where basically it's a combination of a little bit of both. In this sense, is the antisolvent and inverse temperature crystallization, where they call it as a liquid diffuse separation crystallization. What basically means is just they are putting antisolvent into the solution, so they are inducing a super saturation condition before they heated the solution. So they achieve much more faster compared to antisolvent, but a little bit higher quality than the inverse temperature crystallization. The time scale is still in the hours time, like an inverse temperature crystallization. And then after we got the crystal, what should we do? Or we should make it as a device. And since in solar cells, we require certain thickness to efficiently collect the charge, we have to thin down the perovskite itself or single crystal itself. Several methods has been used, such as a top-down approach. We develop it from silicon, community developed it from the silicon industrial process, where they tune down the ingot of the silicon, and they decrease the thickness, or they slice down the crystal into 100 to 200 micrometer size or thick. But in that sense, perovskite has still a little bit much thicker than they are supposed to have, because silicon has indirect properties as a band gap, and perovskite has a direct. So perovskite just need a little bit more thinner than that one. And also the problem of this, the diamond wiring process of silencing or slicing the perovskite is creating a damage on the perovskite surface, and perovskite are prone to defect. And once the defect created, we have to do additional process, which is not really suitable for now. And then the second approach is called bottom-up approach, where they have several methods. One of them is epitaxial growth, where they are growing single crystal from a very high quality or a highly oriented substrate. In this case, it's strontium, STO, strontium oxide. However, it required to have a substrate that is in a very high quality and high order, and it's not really applicable. I mean, what I'm saying is it's not immediately applicable to use for let's say device performance, because it will be limited to the STO substrate to be used for the next purpose of application. And then the last method called space confined growth, where they basically grow based on ITC method. They grow it by the temperature, heating the temperature, and crystallize the single crystal. But instead of allowing them to grow into 3-dimension direction, vertical, horizontal, they limit the vertical direction and allow them only into the into horizontal direction growth. So basically what they did, they limit the thickness based on the distance between these two substrates, that allow them to have a very thin single crystal according to the thickness of the distance between the substrate. And with this method that is developed by my colleague in his previous institute, he grew it in United States, I suppose, at that time, by doing a different coated on the substrate. In this case, they developed with the PTAA, and they found out with the hydrophobic material, they allow them to have a faster ion diffusion movement on this process of called space confined ITC, and therefore they produce much bigger or much better single crystal that can be used for further purpose, such as the solar cells. And they showcases that the size can be up to, in here, lithium lead bromide, centimeter size, and then they can tune the thickness from 10 micrometer to 20 micrometer by changing the distance between these two substrates. As you can see, they measure the absorption spectra, and it keep increasing the range of absorption by increasing the thickness of the substrate. So it's the beauty of single crystal. You can absorb more than the polycrystalline one. And they found out that the optimum thickness for single crystal at that time was about 10 micrometer to make it a device. And then they performed the device with about 18% efficiency at the time. And then, because of this development of space confined ITC, we developed even furthermore from my previous group, which were my PhD institute. We try to develop more the single crystal perovskite solar cell, and nowadays let's say the society can reach of about 25.8% efficiency by this 2025. We are still behind polycrystalline for sure, because polycrystalline has reached 27%. However, if we look up into the trend, we reached 20% in 2019, and polycrystalline reached about 20% PC in 2014. So we actually 5 years behind on what we are supposed to get. So we still have time to improve more in this 5 year. So hopefully we can reach even beyond 27%, because we actually, look, I will tell later on, but we actually benefit much more with single crystal than the polycrystalline one. But unfortunately, what you are seeing in here is not the, like, let's say from the NREL chart, you got everything by certification. But in single crystal, we are not able to still certificate our devices, yet we still produce a record efficiency from the laboratory or from reported work in where it's published in the world. So we're gonna look into a little bit information about how we can come up to 25.8% now. So in my previous institute, especially I think as the host mentioned in CAUS, in my previous group, my colleague developed a new ETL to optimize more for this single crystal perovskite. At that time, they were changing the ETL layer, as you see from here, from PCBM as the ETL blocking layer at the same whole blocking layer into BCP as a whole blocking layer that combined with C60 at the same time. So they found out that by changing this condition of the ETL and also increasing the thickness to 20 micron, they are able to even reach 21% efficiency with single crystal perovskite solar cell. And then they even further improve by changing the composition at the different reported work, by changing from the single cation, in this case, at that time it was still MaPDR3, and then they moved to mixed cation of FAMA, FA 50%, or MA 50%, or FA 60%, MA 40%. They are basically trying to reduce the band gap. So as you see from the right bottom part picture in here, they are changing the band gap from 1.54 into 1.49, I suppose. So basically, lower band gap means you absorb more light. And then that's correspond to higher current density that you see in here. We reach about 26 milliampere per centimeter square. But not only that, because we are moving out from MA, from full MA into half MA, we basically remove the problematic MA, because MA is very it's volatile material whenever you heat it with a high temperature condition, and we crystallize in high temperature condition. So you remove the problematic MA, which makes the defect are much less with mixed cation. So therefore, you got the higher VOC number in this composition. They reach about 22.8%, and that at that time it was a record as well. And then me and my colleague, when I was in my previous place, we tried to modify not the composition at the time. We tried to modify the HDL, because we know we keep getting the reviewer asking for stability test, and then we try to find out how to solve the stability test, because reviewer keep asking this. And then me and my colleague try to modify the HDL layer, and then we come up with a self-assembly monolayer, come from the idea from polycrystalline as well. We change from PTA to MeO2-PAC-Z, that they have basically totally different phenomena, let's say this way. That the PTA is sort of like hydrophobic material, but for MeO2-PAC-Z it's actually hydrophilic material. So with this hydrophilic material, we ended up getting a much bigger crystal of single crystal as a device. And also at the same time, they have a much more strong mechanical addition from the perovskite into the HDL or ITL substrate. And we performed the FD calculation, and it shows that the binding energy in the with the MeO2-PAC-Z is much more stronger than the binding energy with the PTAA. And we performed the device out of this HDL modification. We got slight improvement to 23.1%, that mostly come from the current density improvement, that we believe because we are using MeO2-PAC-Z, which has slightly more transparent than the PTAA and higher current collection in hole collection or hole conduction in compared to PTA. Therefore, they collect current density much more. And then we perform the EKI to confirm the high current density that we have, which reach about 27 at the time milliampere per centimeter square. And what interesting in here, we perform light stability measurement, where in this light stability measurement, we irradiated the devices under one sun for almost 700 hours. I think it's about 40 days, around 40 days. And then it can stays on working as a device for with the efficiency above 75% from the initial one. And we compare with the original HTL that we use, which is a PTAA, which immediately goes to 60% in the first few 10 hours. So it really gives us insight that the HTL play a pivotal role on making the perovskite stable as in the light performance way. And then I tried to come up with an idea how to improve even more the efficiency of the devices by playing around with the composition. We know that MA is a little bit problematic for thermal condition, for thermal, how do you say, the very high temperature condition. Therefore, we tried to change or remove the MA by using a cesium. So we use 5% of cesium and 95% of Fa, with the idea of getting the band gap much smaller than it was it was before. And then it showcases in here that the band gap are even smaller than the FA-MA that we have before, because the smaller band gap means we have a higher current density. But not only that, when we check the crystal by measuring the TRPL, or time resolved photoluminescence, we see that the carrier lifetime are much slower, much longer for cesium Fa compared to the FMA. So it means that the non-radiative recombination in cesium Fa is suppressed compared to the FMA. And we made the device out of this composition, and we got 24.3%. It was a record at the time, 2023. We got 24.3% with a current density of about 28 milliampere per centimeter square. And we also give the EKI measurement that I didn't show in here because of the limited slide number. And also we perform the light irradiance stability that it showcases that under MPP tracking, it maintained for above 75% initial efficiency beyond 45 hours. So I think it's about 20 days, I think 20 days, around 20 days.
Okay, sorry, I disturb you. So you have 6 minutes left for presentation. 6 minutes.
Okay. Okay. Then we also do a thermal stability test, and we obtain that with the cesium Fa we can withstand 53 degrees Celsius by maintaining the initial efficiency of about 90% beyond 100 hours. And then we also furthermore with my colleague, with my collaborator at the time, we try to come up with an idea how to design better for the space confined method, and we come up with the asymmetric method. As you can see in here, we basically has a different coating on the both substrate, and somehow it in situ, the spin coated MO2-PEXY was in situ from the bottom part to the top part. And we checked from the XPS and also FTIR that the MO2-PEXY was exactly present in here. And we found out then with the CV or cyclic voltammetry that the density density of the molecule in the substrate is actually better with in situ coating. So with that, we improve the efficiency more toward 24.3%, but not for cesium Fa, but in that case for FA-MA. And it was the record for FA-MA, 50%. And we check with TRPL, then we confirm that the increased current density and the VOC are coming from efficient hole extraction and reduced charge current recombination. And then later on, we try to improve even more, me and my colleague as well, by adding additional deposition of PMMA on the top of MO2-PEXY, and we check the roughness become smaller. Basically, when you deposit MO2-PEXY, you create some pinhole because of the tendency to agglomerate for MO2-PEXY. So you put additional layer, which is PMMA, to planarize, to fill up the pinhole. And then the surface roughness decrease, and then we confirm the interaction with the carbonyl oxygen with the XPS and also NMR. And then we check the quality of the crystal with TRPL, it improved. We also check the efficiency. We got 25% with FAMA, so that's the record as well for 50% FAMA. And we check also from the TPC measurement that the increase of the current density and VOC are coming from the lower trap assist recombination and efficient current extraction. So beyond that, I also did a lot of some work on single crystal perovskite solar cell as a characterization. We checked that we updated the perovskite to have diffusion length of about 500 micron because we do single crystal perovskite solar cell and we perform well as a solar cells, and we collaborate with our friend in UK at the time. It was Sheffield University, I think. And then they calculated based on that, we updated the diffusion line of about 450. And we also perform the single crystal solar cell as an X-ray detector. We also updated that the sensitivity of this X-ray detector for perovskite to reach about 8 nanogray low dose rate. And then we maintain stability in 14 hours with collaboration with ETH from Switzerland. And then what's next? Actually, just have a very short time. So we need to improve the VOC. If we compare the single crystal and polycrystalline, basically we need to improve the surface and interface of perovskite. And then for stability, based on my me and my colleague review paper, we saw that polycrystalline has already obtained a lot of stability tests, and they are basically integrated stability tests. So they test everything at the same time. But in single crystal, we separate this test. So it's because what we believe we haven't achieved the better encapsulation for single crystal. So it's better if we found this encapsulation method, then we can try to stabilize more in different stressor condition. And then what I was working in University of Stuttgart, I was employed as a postdoctoral researcher. I'm trying to build up the system in the single crystal perovskite starting from phase 1, 2, 3. And then I believe we already achieved the first German institute to reach 20% PCE for single crystal perovskite solar cell. We got 20% with the reference of by replicating the paper of the 21% efficiency. So we basically in the range of the error for single crystal MAPBIT at the time. So we believe with this project, we are going to gain even more efficiency than we are trying to get the record for the single crystal perovskite solar cell from German Institute. Yeah. And then another project in my current places is we are trying to advance perovskite single crystal out the inert atmosphere. So mostly they are growing single crystal in the inert atmosphere, but we are trying to grow it in the ambient condition. And we successfully get 18.77 or around 19% that we grow the perovskite single crystal outside in the fume hood. And then we also, by employing a different HDR in this case, we compare with PTA only get 14%. And we also try to play around with the alkyl ammonium additive, where we try to modify the single crystal by changing different kind of alkyl ammonium. We got much more quality, better quality. In some senses, we increase the current lifetime and also decrease the defect lifetime, and the defect of the perovskite. And I think that's all from my side. I was trying to say that I'm really glad to have this opportunity to talk to you guys. And I'll always say to everyone who listen to me, please join our journey for single crystal perovskite solar cell. Especially, we are in need of a lot of people, especially Indonesian people, to work on a single crystal perovskite solar cell because it's a very rare topic, but it has a lot of potential to do. And I was gladly to have a lot of collaboration with everyone in this symposium, and we can help, and we need an idea as well for making a single crystal perovskite solar cell better and even as the next generation for perovskite solar cell. And I think that's all. You can contact me if you need from this email, and hopefully you can join us. Thanks.
Okay, thank you so much, Dr. Muhammad Naufal, for the comprehensive presentation about single crystal perovskites. Okay, now it's time for Q&A session. So if you, to the audience, if you have any questions, so you can raise your hand or write down on the chat box. So we're waiting from the audience, the question from the audience. So, okay, maybe we have already question from Dr. Yuliar. So, Dr. Yuliar, you can ask directly. Okay.
Hello, Noval.
Hello.
How are you?
I'm good, thanks, Dr.
Okay.
William.
Very nice presentation, and also thank you for accepting the invitation. I have a question actually about the potential for this kind of single crystal materials for scale up. What do you think about it? What is your opinion about the scale up, especially for bottom up technique? Because I remember when we work in Kausi, I remember you made this single crystal in a small scale, right? So is it going to be an issue for making like a large scale device if we want to have it, for example, like for silicon solar cells, or probably it's not needed? So maybe I want to know your opinion about that. And then the second question is, you mentioned that the VOC of this device is increasing, right? I mean, compared to the polycrystalline. But I think the efficiency is still not higher than the record efficiency for the polycrystallines. So maybe you can also comment on that. Why is it the case that the efficiency is still like a little bit lower than the polycrystalline one?
Oh, okay. That's a very good question. I would say that commercialization is not about us as a researcher. It's about how we act as a society. We will never be able to commercialize by myself, by several people. Commercialize always come from many people that work together in this field. But for single crystal, unfortunately, I could find only a few groups want to work on this single crystal. If you say, is it possible to commercialize? For sure, we will be able to commercialize. And I think in the future, we will commercialize for sure. But it's just a matter of time. You want to do it faster or just take longer? Because in the end, if we need, that's what we need now. We need a lot of people to work on these. Like I say, is it possible? It's possible. Can I solve it? I can, but I don't want to solve it because that's not really enticing for now. What I'm saying is I'm trying to solve efficiency-wise now. But if you want to solve commercial-wise, you have to solve another problem, like say, it's why the crystal is small, why it's still not stable. This is the thing that needs someone else to solve it. And the more people we work on this, the more people will try to solve a little bit there, a little bit there. And this will come up with something that is basically is gonna be used by the company later on. Because whatever a company make now is just lower efficiency, but more stable. This is the way it is. But for now, what we need is just, what I'm understanding, what we need is we're gonna need higher efficiency. So people will attract to us, and then we're gonna, once we got attracted more people, then people can start to solve the commercialized one. But for sure, we need to do something for the commercialized one. The second question is VOCPC. Yeah, we still lag behind of the efficiency. I think I mistakenly say to you, but our VOC is still lower than the polycrystalline one. We still have to improve the VOC. And because the surface, I try to understand why, and we come up with the surface problem. So if we try to see the surface of polycrystalline and single crystal, surprisingly, the surface of polycrystalline is much better than single crystal. It's a very strange information for me as well. It has way better bulk compared to the polycrystalline one. But the polycrystalline one has a problem. Single crystal has a problem on the surface part. So nowadays, people, how to improve the efficiency, they just not the only, but the many possibility we can do is first we externally fix it. So we make the crystal and we passivate it. That's one. Second, we inherently change it by the crystallization itself. So what I saw now, what really changed is we change it according to inherent conditions. So we grow, it changed the quality immediately for the grow. That's why I do a lot of like alcohol ammonium additive. This is the way to change the quality of the crystal on the surface immediately by the growing itself. So this is one approach that I do for the increasing the efficiency. But at the same time, this is also a benefit because I always believe, how do I say, like if you have a tire and then your tire is blown, you either have choices. You patch the tire or you change the tire. So passivation means you patch the tire, but it's not really actually helpful because in the end you need a new tire. That's why we are trying to get the crystal immediately from the grow instead of patching it with the, let's say, passivation or whatever. That's why what my intake of this POC.
So you mean that when you because the grain boundary in the single crystal should be better, right? That means
yeah.
Then the problem with the surface is probably the contact. So you will have a worse contact compared to the polycrystalline because the surface is not really good compared to the polycrystalline.
Yeah. It's also interface. Yeah, contact interface. It's also possible because
right.
I think because of the stress as well. I'm not really get into it, but when you have a lot of grain, you basically release some of the strain. And when you release some of the strain, the dangling become less. But with single crystal, you don't have anything to release. So there's a lot of compression stress there. So in the surface, it's just like a lot of dangling. So that's why the defect is just much more on the surface in compared to polycrystalline one. Then it also react when you, let's say you get the interface contact with that with HTL, ETL, because of this a lot of dangling bond, so it just create a lot of defect. Yeah, you're right actually. Yeah, in that sense, yes.
Okay, thank you.
Thanks.
Okay, we have many questions, but before, so maybe I will go to the chat box first. From Adita Asma. So she's curious. So have you ever measured the trap state density of a cell with single crystal perovskite? What kind of measurement did you use to characterize the trap state density, and how about the result?
Yeah, the trap state density, we usually use SCLC to get the trap state of the single crystal. The number is similar, not similar, how do I say? We usually measure that for the bulk, not as a device, but as a inherent bulk crystal. And then what we got is in the number that we mentioned before is about 10 to 12, 10 to 12, 10 to 9 to 10 to 12 trap state of the perovskite.
Okay, so another question. So maybe you can answer shortly because we have limited time, but we have many questions. Okay, for the next question in the chat box, could you share effective strategies for managing nucleation, such as temperature range, solvent selection, or additive use to reduce the number of nuclei and promote higher quality crystal growth?
I think this question comes from someone who works on single crystal. That's why he knows or she knows whatever she's saying. Yeah, so that's what we need to do to control the nucleation. You need to control as much as possible. The less nucleation is better. But at the same time, you have to allow them to have the solution to move fast in that very short distance of the crystallization. So the only way to do, the easiest way to put more volume, but it actually increase the thickness. But in some senses, this is still ongoing progress, and no one actually know the best answer. You have just to try it. So I have to answer very quick. Sorry.
Okay, okay, okay. So another question. Maybe from Mr. Yuda who raised hand. So you can ask directly with short question.
Okay, thank you so much. Thank you so much for Dr. Naval for very interesting talk. So basically, I just want to ask a very short questions. You show about the what do you call the depth or the thickness dependent. How if you you tune the thickness of the single crystal perovskite, so you can tune the wavelength bandwidth. So basically, could you please just briefly explain the intrinsic phenomena behind this phenomena, sir?
Yeah, it's a very good question. So what we know that in perovskite they have two parameters to absorb. First is the direct process, because when you see in the band structure, there are two possibility of direct absorption or direct band gap, and the other in indirect band gap. Usually for perovskite, you have these two properties, the direct and indirect. Sorry, the direct comes from the normal band gap that we use, but the indirect can only be accessed if you have much thicker. So you don't see it in the polycrystalline one, because the absorption coefficient for this indirect is super small. So you have to have thicker one, then it shows up. So that's why when you have a thicker one, somehow this indirect band gap give us the additional collection. That's why you get a little bit shift in that sense.
Okay, thank you so much.
Yeah.
Okay, another question in the chat box, but maybe I will okay in the chat box. Okay, thank you for the presentation. So if I sort the question, so why do you claim your perovskite is single crystal? Why use hybrid organic inorganic perovskite instead of all inorganic, which can improve band gap and PCE? Since MA stability is poor, why do you done MA with FA, then add CS to FA instead of using cesium directly as the A site?
Okay. So single crystal means that it's not about the composition. The composition itself can be Fa, Ma, cesium, mix, or whatever. But the single crystal comes from the structure, from the like I mentioned before, the bulk structure, whether it has grain or not. So let's say if we have cesium in Fa, it doesn't mean it's not going to be single crystal. It can be single crystal as long as it doesn't have grain. In that sense, the question is why I changed the composition. For sure, every element has a problem. Let's say if you use Ma, they are prone to temperature. So if you use Ma, when you heat it, it will evaporate, and then you will not have the same composition, and you will not produce a device anymore with that temperature. We remove Ma, we put Fa. But Fa has problem. It become yellow in room temperature. And then that's why we put additional elements, let's say cesium or rubidium, to stabilize them at room temperature. That's how we come up with this composition. Regarding pure cesium or inorganic is stable, is very good, but the problem is cesium lead bromide, especially cesium only, they are not very good as crystallizing because of the problematic of cesium with the very heavy atom. So that's why we try to find like the optimum one. For sure, inorganic must be the best for stability, but still to perform a good crystal is still underway, I think.
Okay, so I think we have last question because the limited time. So may I know what is the yield of the reaction of making single crystal? If we put the yield and if we put 1 gram precursor, how much maximum we get the crystal?
The yields usually in the range of 10%, the yield of single crystal. But what we are talking here is the yield of bulk single crystal. We're not talking about as a device. As a device, I never count the yield of as a device. Let's say after I crystallize, I check the mass of this. No, I never did it, but as long as I know, usually with ITC the yield is about 10%. With different method may give you a different yield.
Okay, thank you so much for the presentation and answer the questions. We already have reached 40 minutes, so I think I'd like to say thank you for the nice and comprehensive and very interesting presentation. So please give applause to our keynote speaker. Okay, thank you so much. And thank you so much for sharing your research, okay? And please give applause again. So, okay, thank you. So I think now we are in the end of the session. So before end the session, so let me make some little conclusion that single crystal perovskite offers promising prospects for the next generation of solar cell. And at the end of the sessions, I would like to say my sincere thanks to all the presenters and to the audiences. And now I hand the event back over to the MC, Miss Fia.
Okay, thank you, Dr. Nunik and also Dr. Noval for great session. Ladies and gentlemen, we have come to the final part of today's program. Please welcome Professor Yusuf Nur Wijayanto to deliver the closing remark. To Professor Yusuf, the screen is yours.
Okay, thank you very much, Ms. Via, for the time. Okay, for the distinguished guest speaker, young speaker, participants, and organizing committee, and all colleagues. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon in Indonesian. Yeah, this is it's time to conclude and close the second symposium on Advanced Photovoltaic 2025. Okay, let me express my deepest gratitude for your time, insight, attractive discussion, and great contribution throughout this symposium. In these past 2 days, this is an interesting day for us, and here we can discuss anything relating the solar cell. We have exchanged knowledge and learning many new things, which hopefully will help accelerating next generation photovoltaic solution for a cleaner and brighter in the future. In this second symposium, the theme is relating the recent progress and challenges for next generation photovoltaic technologies. It's cover various aspects from novel materials and device architectures to reliability and manufacturability and also other potential application. During this symposium, we can get important things such as the novel, the new knowledge and recent progress relating the themes, and also recent research partnership and collaboration from this symposium. We hope to gain strategic collaboration between academia, industry, and government. With this spirit, allow me a clear call to action. Let us revitalize and activate the Indonesian solar energy research activity. We invite you all of you to help make ACERS a living working forum, one that coordinates national working group on solar energy material, reliability, and also system. I also invite you all to collaborate with Research Center for Electronic Brain, where we are equipped with state-of-the-art electronic devices infrastructure, such as a solar cell laboratory and also clean room laboratory. On behalf of the Research Center for Electronic and Research Organization for Electronic and Informatic National Research and Innovation Agency, I would like to thank our organizing committee, session chairs, and also above all our speakers and participants. Your contribution have made this second symposium not just a meeting, but a momentum. I encourage you all to stay connected, propose joint project, and bring your institution into ICER's activity so that an impactful collaboration could be realized to give significant impact in the Indonesian solar energy research community. Thank you, everyone. Please stay and healthy and happy always until we meet again in our next gathering. May the collaboration formed today help power and sustainable future for Indonesia and beyond. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Prof. Yusuf. Ladies and gentlemen, we have now reached the end of the second symposium on Advanced Photovoltaic 2025. On behalf of organizing committee, I would like to express our deepest gratitude to all keynote and invited speakers, session chairs, young scientists, and all participants for joining us these 2 days. We hope this symposium has been inspiring and will lead to stronger collaboration in the future. Thank you and see you at our next symposium. Have a wonderful day. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you very much.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much. Terima kasih semuanya.
Oke.
Terima kasih.